Usually when we talk about making a choice between two incredibly complex things, we really crave a simple metric.
Right, a shortcut. We always want a shortcut.
Exactly. I mean, imagine you were comparing two massive investment portfolios for a client. You don't just want to know which one made more money yesterday because, well, yesterday's already gone.
Yeah, past performance doesn't guarantee future results, as they always say.
Right. You want to know fundamentally, structurally, which one is riskier across all possible future market conditions. Or think about a lead actuary sitting at a desk looking at two entirely different insurance risk profiles for two different cities.
Oh, that's a nightmare scenario.
It is. Comparing them is incredibly difficult, brutal mathematical work. Historically, you're forced to map out every single possible disaster, every hurricane, every fender bender, every slip and fall point by point, and then weigh them against each other on this massive scale.
Which takes an unbelievable amount of computing power and time.
Exactly. But what if there were a single underlying kernel, like a math or mathematical shortcut, that instantly told you which one was riskier without doing hours of those brutal point-by-point calculations?
I mean, that is the holy grail for anyone working in probability theory or risk management.
Okay.
Oh, absolutely. We spend our professional lives just drowning in data trying to prove that scenario A is definitively mathematically worse or riskier than scenario B. And for decades, the computational tools we've had to accomplish that proof have been, frankly, exhausting to use.
Just clunky.
Extremely clunky. They require an immense amount of algebraic heavy lifting that often just breaks down the moment real-world data gets messy.
Well, today we are exploring a tool that completely upends that heavy lifting. Welcome to today's deep dive. We are unpacking an incredibly dense, genuinely groundbreaking piece of advanced statistics titled Kernel Characterizations of Stochastic Orders Within Parametric Density Families.
Fascinating paper.
It really is. It was written by Zakaria Derbazi and published on May 19th, 2026. And the mission of this deep dive is to unpack exactly how Derbazi uses what he calls kernels to create this master shortcut for comparing probability distributions.
And we should warn you, we are going to get into the weeds here.
Oh, definitely. We are going to see how a seemingly abstract mathematical trick, specifically taking the derivative of a log density, can unlock the foundational behavior of random variables.
Right.
So whether you are a data scientist building predictive models, an actuary pricing catastrophic risk, or just someone who, loves finding elegant solutions to messy real-world problems, this deep dive is going to fundamentally change how you think about shifting dials in statistical models.
The crucial thing to understand right out of the gate is that Derbazi isn't just offering a minor computational tweak to an old formula.
Okay, so it's bigger than that.
Much bigger. He is introducing a completely unified framework. Before this paper, the field of statistics treated different types of risk comparisons as completely separate mathematical disciplines.
Like they didn't even talk to each other.
Basically, yeah. They required entirely different sets of proofs. Derbazi shows that they are all actually connected by this one single thread, the kernel.
Okay, well, let's lay the groundwork before we get to the magic of the kernel itself. We need to understand the baseline of what we are actually comparing here. The paper focuses on 4 stochastic orders.
Right, the hierarchy.
Yeah, and let me stop and clarify that jargon right away for you listening. When we say stochastic ordering, we are really just using the rigorous mathematical way of saying this random thing is definitively bigger or worse or riskier than that random thing.
That is the perfect translation, honestly. We use the word stochastic because these aren't fixed numbers.
Like a static bank account balance.
Exactly. If I have 5 apples and you have 3 apples, 5 is greater than 3. That's deterministic. It's a certainty. But if my investment portfolio might return anywhere from negative $10,000 to positive $50,000, and yours might return anywhere from negative $5,000 to positive $20,000, simply saying mine is greater than yours doesn't make any sense anymore.
Because the ranges overlap so much.
Right. We have to compare the probabilities of all those potential outcomes happening. That is what stochastic ordering is. And the paper focuses on a strict hierarchy of 4 specific ways to do this.
Let's start with the most intuitive one on the bottom of that hierarchy, the usual stochastic order.
So the usual stochastic order simply means that one random variable is, generally speaking, yielding larger outcomes than another.
Okay, let's use the investment portfolio example again to ground this.
Good idea. So if you pick any threshold, let's say, the probability of an investment losing more than $10,000, the riskier portfolio will always have a higher probability of crossing that threshold than the safer one.
No matter where I draw the line.
Exactly. That rule has to hold true no matter where you draw the threshold line. If it holds everywhere, portfolio A stochastically dominates portfolio B.
That makes perfect sense. It's just the baseline definition of one thing being systematically worse or larger. So that covers the first order. Have we missed any nuances there before moving on?
I think we've thoroughly unpacked it. It's the most straightforward one. Let's proceed to the next concept.
Okay, what is the second order in the hierarchy?
The second is the hazard rate order. And this one is absolutely vital in things like reliability engineering and medical survival analysis.
Like testing how long a pacemaker will last?
Exactly like that. It compares the conditional probability of immediate failure. Imagine you have two massive industrial machines operating in a factory, and both of them have successfully survived for exactly 5 years without breaking down.
Okay, so they're tied so far.
Right. But the hazard rate order doesn't care about the total lifespan anymore, it asks. Given the specific condition that they've made it this far, which one is more likely to break down in the next 5 minutes?
Oh, I see. So it's constantly updating based on the present moment.
Yes, it's instantaneous. If machine A always has a higher immediate instantaneous risk of failure than machine B, regardless of whether we check it 5 years, 10 years, or 20 years, then machine A dominates machine B in the hazard rate order.
It implies a constant looming threat that always outpaces the alternative.
That's a great way to put it.
Okay, so the usual stochastic order is about overall cumulative probability, and the hazard rate order is about immediate conditional doom.
Right.
That brings us to the third one, which Derbazi really centers in this paper, the likelihood ratio order.
This is the big one. It's the strongest, most mathematically demanding comparison of them all. This is a strict point-by-point comparison of the actual shape of the distributions.
What does that mean in practice?
It essentially dictates that as you move further out into the extreme outcomes, let's say,
Hmm.
looking at increasingly devastating hurricane damages, the ratio of the probability of the worse model happening compared to the better model happening is constantly increasing.
Wait, constantly increase.
Yes. It means the worst model isn't just riskier overall, it gets exponentially more dominant the further into the extremes you go.
Let me make sure I'm grasping the hierarchy here. If you can mathematically prove this likelihood ratio order, does that automatically guarantee the other two?
It does. That's why it's so important. It is the gold standard. Proving likelihood ratio dominance automatically implies hazard rate dominance, which in turn automatically implies usual stochastic dominance.
Wow.
Yeah, that's why actuaries and statisticians are so desperate to prove the likelihood ratio order. It is the ultimate mic drop in risk analysis.
There is a fourth one mentioned in the text, relative log concavity. Let's just quickly define that before we move on.
Relative log concavity is slightly different. It's less about one distribution being strictly larger and more about comparing the shape, the spread, and the variance of the two distributions.
Like how wide the bell curve is.
Exactly. It tells us how the tails of the distributions behave relative to one another, essentially. How thick the extreme ends are compared to the center. It's a measure of unpredictability and structural risk.
Let me stop you there and ask a skeptical question that you, the listener, might be thinking right now. Why do we even need all these specific, rigid mathematical orders?
That's a fair question.
I mean, if I'm a business owner trying to decide between two insurance policies or two manufacturing processes, can't I just look at the average expected loss?
You could, but
Like, if process A loses an average of $1,000 a day and process B loses an average of $2,000 a day, why go through the grueling mathematical pain of proving likelihood ratio dominance? I just pick process A.
and that is the exact trap that causes businesses to go bankrupt.
Really?
Oh, absolutely. Averages are inherently deceptive.
Right.
An average completely masks catastrophic tail risks.
Okay, walk me through that.
Let's say you are a pension fund managing billions of dollars, or a civil engineer designing a suspension bridge. You cannot afford to just be better on average.
Right, because if a bridge fails once, it's game over.
Exactly. Process A might have a lower average loss because it has a lot of zero loss days. But once every 10 years, it might trigger a total catastrophic $100 million meltdown.
Oh, I see.
And process B might lose a steady $2,000 a day every day. But it structurally cannot melt down. If you just rely on the average, you choose process A, and eventually your bridge collapses.
That paints a terrifyingly clear picture. You need absolute certainty across the entire landscape of probability, not just a snapshot of the middle.
Precisely. You need to mathematically prove that under all possible worst-case scenarios, your new model is structurally safer than your old model.
And historically, to prove this absolute certainty, researchers had to manually calculate the likelihood ratio. Let me explain what that actually entails, because it's a nightmare.
It really is.
You have to take the dense, incredibly complex algebraic function that describes the first distribution. Then you take the equally complex function for the second distribution. You literally divide one by the other to create this massive, ugly fraction.
It's a wall of math.
Yeah. And then you have to use calculus to prove that this new monstrous ratio function is constantly increasing across every single possible data point from 0 to infinity.
Which sounds bad enough, but in practice, it's notoriously clunky. It requires integrating over messy functions, dealing with normalizing constants.
Wait, what's a normalizing constant?
Ah, right. So a normalizing constant is just this massive mathematical anchor required to make probabilities add up to exactly 100%. If you have a curve, the total area under that curve has to equal 1. The normalizing constant forces that to happen.
But it makes the algebra worse.
So much worse. Quite often, the algebra simply hits a wall. The equations become too complex to solve by hand, or even by standard computational methods.
And this is exactly where Zakaria Derbazi steps in. Instead of taking two different distributions and mashing them together into a giant, unwieldy ratio, Derbazi says, let's look at one single distribution and watch what happens to it when we turn a single dial.
Yes.
He introduces two concepts that form the absolute bedrock of this paper: the score and the kernel.
The underlying shift in perspective here is brilliant. Derbazi utilizes a classic mathematician's trick, but he applies it in a very novel way. Let's start with the score.
Okay, let's break that down.
To find the score, you take the probability density function, which is just the mathematical curve describing your data, let's call it f theta, x, f sub theta of x, and you take the natural logarithm of it.
Let's explain why a mathematician would do that. Taking the natural logarithm isn't just to make the formula look fancy, right? It fundamentally changes how the numbers interact.
It changes multiplication into addition and division into subtraction. That's the key.
So it flattens it out.
Exactly. Simplex probability distributions are often built on strings of variables multiplied together. By taking the natural log, you unschool all that tangled multiplication into a clean line of addition.
That makes it so much easier to work with.
It does. Once he has the log density, Derbazi takes the derivative of it with respect to a specific parameter. In mathematical notation, it's frac partial derivative with respect to theta of the natural log of f sub theta of x.
Okay, let's unpack parameter and derivative for anyone listening who hasn't taken calculus recently. A parameter is essentially the dial we are turning.
Right.
If we are looking at a factory's defect rate, the parameter might be the speed of the assembly line. If we are looking at investment returns, the parameter might be the percentage of the portfolio held in volatile tech stocks.
Correct. The parameter, which we call theta theta, is the underlying cause, the dial you control or observe.
And the derivative.
The derivative is simply the mathematical measure of sensitivity. Taking the partial derivative with respect to that dial tells us exactly how sensitive the probability of any specific outcome is when you slightly turn that dial.
So that's the score. But what about the kernel? How's the kernel different from the score?
The kernel is the final refinement. Remember that ugly normalizing constant we mentioned earlier?
The mathematical baggage needed to make the total area equal 1.
Exactly. The derivative of that constant doesn't depend on the actual data outcome. It only depends on the dial itself. Derbazi defines the kernel, denoted as connex k sub nu of x, as simply the score minus the centering term.
So he just chops it off?
He strips it away. By removing that constant, the kernel isolates the pure, raw, unfiltered behavior of the distribution shape as the dial turns.
Let me try a sports analogy to really ground this concept.
Yep.
Imagine we are trying to compare two baseball players to see who is fundamentally more valuable. The traditional likelihood ratio approach is like comparing them by looking at a massive, complex spreadsheet of thousands of individual game stats, hits, walks, pitch velocity, weather conditions, stadium altitude, and trying to mathematically cross-reference every single cell against the other player's cells.
That sounds overwhelming.
It is overwhelming, but the kernel approach is entirely different. It's like finding a single unified metric, like WAR, wins above replacement, that isolates exactly how changing a player's training regimen, which is our parameter dial, changes their overall fundamental value to the team.
I like this.
You don't need to cross-reference the massive spreadsheet anymore. You strip away the noise, you find the underlying metric, and you just watch how the WAR shifts when the training dial is turned.
That analogy actually tracks perfectly with Derbazi's math, because war isolates the individual player's impact from the normalizing constant of their teammates' performance. The kernel conu x k subnu of x isolates the effect of the parameter without getting bogged down by the overall size or shape of the entire probability space.
Okay, so I think we've really thoroughly covered the baseline there. Are there any other nuances about the score or the kernel we missed?
No, I think we've unpacked that section completely. We've got the definitions locked down.
Great. So we've established what the kernel is, but the crucial question is, how does this single elegant metric actually connect back to those four heavy-duty stochastic orders we defined earlier?
Right, how do we use it?
This leads us to the core framework of the paper, the density, survival, and hazard identities.
To build this framework, Derbazi relies on two foundational mathematical engines in the paper, Proposition 3.3 and Lemma 3.4.
And what do those do?
On the page, these look like dense blocks of calculus, but their function is breathtakingly elegant. They establish that the derivative of the log survival function is simply equal to the conditional expectation of the score.
Let's translate that. The survival function tells us the probability of surviving past a certain point, like our factory machine lasting longer than 5 years.
Yes.
You're saying that to find out how that survival probability changes when we turn our dial, we just look at the expected average of the score.
Yes, but with one critical caveat. You only look at the expected average of the score given that the random variable is greater than our threshold. Mathematically, it's represented as e nu x stack. X mimics the expected value of k sub nu of x, given that x is greater than or equal to x.
Wait, I need to challenge this.
Sure.
Lemma 3.4 says we bypass the whole distribution and only look at the tail conditional mean. If I'm an engineer evaluating the safety of a bridge, you're telling me to ignore 90% of the normal everyday traffic data and only look at the mathematical average of the extremes.
Basically, yes.
How is that mathematically safe? Aren't we throwing away vital context?
It seems highly counterintuitive, I know, but you aren't throwing away context. The math is actually perfectly preserving the context of the extremes. Because of the way probability works, the total survival probability inherently depends only on what happens after the threshold.
Oh, I see. Because if you've already survived to year 5, years 1 through 4 don't matter anymore.
Exactly. Lemma 3.4 is a masterclass in simplification. It expresses the complex derivatives of the density function, the survival function, and the hazard rate strictly as differences between the pure kernel function evaluated at a specific point, k sub no of x,
Yeah.
and its tail conditional mean, e key x, the expected value of k sub no of x, given that x is greater than or equal to x.
So you don't integrate the ratios at all.
You entirely bypass the gruesome integration of likelihood ratios. You were just comparing a single point on the kernel to the average of the kernel's tail.
But mechanically, how is this legal mathematically?
What do you mean?
Because anyone who has taken college calculus knows that taking derivatives inside of integrals, which is what you are doing when you calculate these expected averages as the dial turns, can lead to massive, catastrophic errors if the data behaves unpredictably. You can't just swap the order of operations whenever you feel like it.
You're talking about differentiation under the integral sign. That brings us to the regularity condition, explicitly mentioned in the text. This is a crucial safety protocol built into the theorem.
So there are guardrails.
Very strict guardrails. For this elegant shortcut to be mathematically legal, the probability distribution has to behave relatively smoothly when you tweak the parameter. We can't have wild, infinite jumps in probability just because we turn the dial a microscopic amount.
So we need to ensure the math doesn't explode.
Exactly. To guarantee this, Derbazi stipulates that there must be what's called a majorant function.
A majorant function. Let's define that.
Think of a majorant function as a mathematical ceiling. It is a stable overriding curve that sits above your actual data curve and bounds the derivative.
Caps it.
Right. As long as the derivative of your probability distribution always stays safely underneath this ceiling, the math remains stable. It allows you to use a classic rule often referred to in physics as Feynman's trick, or Leibniz's rule, which lets you legally pass the derivative operator inside the integral sign.
I remember Feynman talking about that.
It's a brilliant trick. It rigorously locks in these identities without violating the fundamental laws of calculus.
So, to put it simply, as long as our factory isn't spontaneously exploding when we adjust the machine's speed by a fraction of a percent, as long as there is a predictable ceiling to the chaos, the math holds perfectly.
Precisely. And with those foundational identities mathematically locked in and proven safe, I think we're ready to move on. Have we fully covered the density and hazard identities?
Yeah, we've broken down Lemma 3.4. I think we are ready for the main event. because with this proven, Derbazi is ready to unveil the massive breakthrough of the paper, Theorem 3.5. This is the unified four-order characterization.
This is truly the crown jewel of the paper.
Theorem 3.5 provides 4 critical proofs that show exactly how the simple visual shape of the kernel determines the complex stochastic order. Let's walk through them one by one, because this is where the shortcut fully materializes.
Okay, let's do it.
Number 1, if the kernel is a non-decreasing function, you automatically get the likelihood ratio order.
Think about the power of that statement. You don't need to divide two messy formulas. You graph the kernel, kx, k sub, of x. If the line always goes up from left to right, if it is globally non-decreasing, it means that turning the parameter dial always shifts the weight of the probability consistently toward higher outcomes across the entire board.
And that instantly proves likelihood dominance.
Instantly. No intervals required.
That's incredible. Let's go to number 2. If the kernel is concave, you get relative log concavity. And by concave, we mean it looks like an upside-down bowl, right?
Yes. It might be increasing, but it's slowing down, or it might be decreasing and accelerating downward.
So the curve is bending downwards.
Right. The concavity of the kernel directly and necessarily translates to the log concavity of the likelihood ratio. A concave shape structurally restricts the variance. It pulls the extremes inward, controlling the thickness of the tails. If you see an upside-down bowl shape in the kernel, you immediately know the relative spread of your risk is contained.
Okay, number 3. If the tail conditional mean of the kernel is greater than or equal to the overall mean of the kernel, you get the usual stochastic order.
Let's dig into the mechanics of that because it is incredibly intuitive once you visualize it.
Go ahead.
It says that if you look at the extreme right tail of your data, the worst-case scenarios, and the expected average value of your kernel in that specific extreme zone, xx, x, x, xx, the expected value of k sub n of x, given that x is greater than or equal to x, is higher than the average value of the kernel across the entire normal data set.
Then what?
Then turning your dial definitively makes extreme outcomes more likely. Therefore, the new distribution stochastically dominates the old one.
That makes perfect logical sense. And finally, number 4. If the specific value of the kernel at any point x is consistently less than or equal to the tail conditional mean past point x, you get the hazard rate order.
Which means the risk of immediate failure at any given moment is dropping relative to the accumulated future risk.
Right.
But what's truly fascinating here isn't just the rules themselves, but the logic Derbazi uses to prove their absolute necessities. He uses a method of continuity and contradiction.
Oh, this is the bump proof. We have to explain this visual to the listener because it's brilliant. Walk us through what happens if we violate the rule.
Okay, let's focus on the first rule. To get likelihood ratio ordering, the kernel k sub nu of x must be perfectly globally non-decreasing. It must always go up.
No exceptions.
Right. To prove this must be true, Derbazi essentially says. Let's pretend it's not. Let's assume we have likelihood ratio dominance, but we have a kernel with a small defect. There is a tiny localized section where the kernel briefly dips down a mathematical bump in the wrong direction.
A pothole on our otherwise smooth upward road.
Exactly. Now, because the log likelihood ratio is fundamentally the accumulated area of the kernel as you move along the parameter path, that little pothole has a devastating consequence.
Because it subtracts area.
Yes. As you accumulate the area over that dip, that mathematical bump in the kernel will eventually force the overall likelihood ratio to flip directions. It will stop increasing and start decreasing.
And that breaks the definition.
It completely contradicts the core definition of the likelihood ratio order, which states the ratio must always increase. Therefore, through contradiction, Derbazi proves that for the order to hold true across the entire infinite landscape of data, the kernel absolutely cannot have any bumps, dips, or potholes. It must be globally non-decreasing.
I really want you, the listener, to grasp how incredibly powerful this reduction is. You no longer have to juggle 2 massive conflicting risk landscapes on your desk, dividing them and agonizing over the resulting integrals. You simply isolate the kernel of one single distribution and you look at its shape as you twist the dial.
It's beautiful.
If the shape goes up, you have likelihood dominance. The computational friction is practically eliminated.
To demonstrate how beautifully this works in practice, Derbazi provides Table 1 in the text. He applies this theorem to what we call classical exponential families.
What are those exactly?
These are the absolute workhorse distributions of modern statistics. The normal distribution for bell curves, the gamma distribution for wait times, the Poisson distribution for counting events. When you apply Derbazi's math to these families, the kernel collapses into something breathtakingly simple. It becomes nothing more than the sufficient statistic.
Let's define sufficient statistic for those who haven't taken a stats class recently. It's essentially the piece of data that contains absolutely all the information you need to estimate the dial you are turning, right?
Exactly.
If you are looking at a normal distribution, the sufficient statistic is just the sample mean. You don't need every individual data point. The mean gives you everything you need.
Right. For an exponential family, the grueling calculus beautifully collapses into itself. The kernel is the sufficient statistic. So if the sufficient statistic is a function that increases, which it usually is, often just being the variable x itself, you immediately, instantly have your likelihood ratio ordering.
No integrals required at all.
None. You just look at the formula, see a positive variable, and definitively state this risk profile mathematically dominates the other.
So does that fully unpack Theorem 3.5? Have we missed any logic on the unified orders?
I think we've nailed it. The four rules and the proof by contradiction are the core of it.
Okay, well, I have to play devil's advocate here.
I expected nothing less.
This framework works perfectly when the kernel has a nice, smooth, ever-increasing shape. It works beautifully on clean, textbook exponential families, but the real world is almost never a clean exponential family. Data is messy.
Very true.
What happens when the kernel is not simply going up or down? What if it wobbles? Does this entire elegant theory just fall apart? That brings us to section 4 of our deep dive, breaking the rules.
It's the most important question to ask, and section 3.3 of the paper tackles it head on. Global shape properties like demanding a line is always increasing or always concaves fail constantly in real-world modeling.
Because reality isn't a straight line.
Exactly. Sometimes the whisk increases initially as you turn the dial, but then it plateaus or dips. If the kernel k sub nu of x goes up, hits a peak, and then goes down, we can no longer use the simple likelihood ratio test from Theorem 3.5. The core assumption breaks.
But Derbazi doesn't surrender here.
No, he doesn't.
He introduces a workaround that he calls the super-level set criterion, which is proposition 3.7. And here's where those tail conditional means the expected averages of the extremes we talked about earlier come back to save the day.
Yes. Derbazi proves that even if the kernel is non-monotone, meaning it wobbles, it goes up and then down, as long as the score starts off positive and only crosses the zero line exactly once, moving from positive to negative, we can still mathematically prove hazard rate and usual stochastic ordering.
Let's expand our sports metaphor to really visualize this super-level set. Think of a marathon runner. We want to mathematically prove that runner A will definitively beat runner B. The strict likelihood ratio order requires runner A to be constantly accelerating, running faster at every single mile marker than the one before it.
Which is physically impossible.
Right. Runner A is human, and eventually around mile 20, they hit a wall. Their speed, which is our kernel, goes up initially, but then it definitively goes down. Traditional likelihood math says we can no longer guarantee a win, but the super-level set criterion looks at the data differently.
How does the marathon map to the criterion?
The super-level set criterion essentially says, let's look at runner A's initial burst of energy, their glucose levels, their early heart rate. As long as that initial burst is massive and positive and their speed only drops off once predictably without erratic, chaotic fluctuations back and forth, you can mathematically guarantee they have banked enough time to still beat a slower, steady runner overall.
Well, that's good.
Even without perfect, continuous acceleration, their initial dominant lead, the super-level set, secures the overall stochastic order.
That is an excellent visualization of how the math functions.
Yeah.
The initial positive set, the super-level set, carries enough heavy statistical weight to permanently dominate the tail, even when the tail dips.
It banks the dominant.
Exactly. And Derbazi applies this specific criterion to some of the most incredibly stubborn, frustrating statistical problems in the field, specifically focusing on zero-inflated laws, which he outlines in detail in examples 4.4 and 4.5.
I love the zero-inflated examples. Let's make this concrete with the zero-inflated Poisson law. Imagine a factory manufacturing advanced microchips. Normally, the number of defective chips per hour follows a standard Poisson distribution. It's a nice, predictable, smooth, bell-like curve. But occasionally, maybe once a week, the factory manager just turns the entire machine off completely for maintenance. During that hour, you have exactly 0 defects. When you look at your overall data for the month, you have a normal curve, but with a massive, unnatural, towering spike precisely at the number 0. It is zero-inflated.
And that massive spike at 0 is a complete nightmare for traditional mathematical comparisons.
Why does the spike break the math?
Well, if you try to compare a factory with a 10% shutdown rate to a factory with a 5% shutdown rate using the traditional old-school likelihood ratio, the math literally explodes. Because at the exact coordinate of 0, the ratio between the two factories jumps drastically upward, instantly breaking the golden rule that the likelihood ratio must be constantly decreasing or increasing without bumps.
Because 0 creates a massive divide by 0 or massive ratio jump scenario.
Yes, the order fails. Traditional actuaries would just throw up their hands.
But Derbazi's kernel approach bypasses the spike. How does it avoid the explosion at 0?
Because Derbazi's criteria for hazard rate and stochastic orders rely entirely on those tail conditional means. Remember lemma 3.4, ek nu x, the expected value of k sub nu of x, given that x is greater than or equal to x. When you evaluate the expected value of the kernel, given that the defects are greater than or equal to 1, you are mathematically stepping right over the atom at 0.
You just ignore the massive spike.
You step right over it. The mathematical criteria neatly sidestep the 0 jump entirely. Through rigorous proof, Derbazi shows that despite the massive unnatural anomaly at 0, these zero-inflated distributions still perfectly obey stochastic and hazard rate orders as you change the underlying defect rate.
It's a phenomenal demonstration of just how robust the kernel approach is when faced with messy, broken data.
It really proves the framework works outside the textbook.
Okay, so that covers section 3.3 in the super level set. Is there anything else about breaking the rules we should add?
I think the zero-inflated Poisson example perfectly illustrates the why and the how of it. We can move on.
Okay, this is all incredibly elegant for a closed system, but the real world rarely lets you tweak just one variable at a time.
Very true.
What happens to this beautiful math when we are forced to twist 3 or 4 dials simultaneously? If our machine has a whole control panel of interacting dials, does the single kernel concept just fall apart? This takes us into section 5, multi-parameter paths and interpolations.
This is covered in sections 4.3 and 4.4 of the source material. When multiple parameters vary together, the initial assumption is that the framework breaks, because Derbazi originally defined the score strictly as the derivative with respect to a single parameter.
Right.
But he proves that the exact same foundational logic applies by using what he calls a path kernel.
And what are the mechanics of building a path kernel? How do we combine the dials?
It relies on the chain rule from multivariable calculus. If you have a multi-parameter family, a control panel with many dials, you mathematically construct a specific path through that parameter space. The path kernel is then simply a weighted combination of all the single parameter kernels.
So you add them up.
You isolate the kernel for dial A and multiply it by the specific rate of change of dial A. You do the same for dial B and dial C, and you add them all together.
So it's essentially like putting weights on a massive scale. You isolate the individual sensitivities, figure out how fast each dial is turning relative to the others, and mix them into a single master equation.
Precisely. And by combining these single parameter kernels along a path, you can execute comparisons between highly complex, entirely different distributions. Derbazi details this extensively in example 4.8, where he uses the path kernel to interpolate from a beta binomial distribution directly to a pure binomial distribution.
Wait, hold on. A beta binomial and a pure binomial are completely different animals structurally.
They are.
A binomial distribution assumes the probability of success is absolutely fixed, like flipping a rigged coin where you know it lands on heads exactly 60% of the time. A beta binomial assumes the probability of success is itself a random variable, like pulling a rigged coin out of a giant bag of variously rigged coins and then flipping it.
That's a perfect description of the difference.
Are you saying Derbazi's math allows us to build a mathematical bridge between two fundamentally different models of reality and watch the kernel transform as we cross the bridge?
Yes, that is exactly what the interpolation achieves. And the brilliance is that he does it without ever needing to write out an explicit, cumbersome, multi-page path equation. He utilizes the log factor ratio.
How does that work?
If the two distinct distributions share a compatible underlying mathematical structure, which they almost always do within these statistical families, the path kernel mathematically simplifies into the logarithm of the ratio of their parameter-dependent factors. The log factor ratio acts as an invisible, flawless bridge between the two realities.
That immediately makes me think of the Katz class pairs discussed in example 4.9.
Oh, that is the perfect application of the bridge. The Katz class is a specific family of distributions that includes the binomial, the Poisson, and the negative binomial distributions.
A whole family of them.
Right. Historically, If an actuary wanted to prove that a binomial distribution was log concave relative to a Poisson distribution, it involved incredibly tedious brute force algebra. But with Derbazi's unified path kernel approach, you simply look at their coefficient ratios.
Just the ratios.
Yes, because all the distributions in the CAS class share a generalized power series representation. All the heavy, complex math naturally cancels itself out when you build the bridge. You are left with a surprisingly simple ratio of their underlying coefficients.
That's wild.
You look at that single ratio, check if it's concave or increasing, and you immediately prove the stochastic order between two entirely different families of distributions.
It's like discovering a universal translator for probability languages. You don't need to speak fluent binomial and fluent Poisson to compare them. You just translate them both into the foundational language of the kernel and compare them there.
I couldn't have said it better myself.
So I think that covers the multi-parameter interpolations. Does that all track?
Absolutely. The log factor bridge is the key takeaway there.
So far, we've looked at fixed formulas, we've dealt with zero-inflated anomalies, and we've built bridges across multiple dials. But for our final exploration, we need to push the boundary even further.
Into the unknown.
What if the dials are turning themselves? What if the parameters aren't fixed numbers at all, but are themselves random variables? This takes us to section 6 of the paper, compound laws.
This is arguably the final, most significant major contribution of the paper, found in section 3.4. Compound laws deal with the absolute chaos of summing up a random number of random variables.
Let's give a highly specific real-world example so we don't get lost in the abstraction of random sums. Let's go back to our actuary at the insurance company. Every single month, the company receives a random, unpredictable number of car crash claims. That is the first random variable, the frequency or the count.
Okay, yes.
But then every single one of those individual claims has a totally random, unpredictable payout amount. One might be a $50 scratched bumper. Another might be a $500,000 total loss with medical bills. That is the second random variable, the severity.
Right.
A compound law represents the total amount of money the insurance company pays out at the absolute end of the month. It is a random sum of random severities.
And predicting the behavior of compound laws is notoriously exceptionally difficult because the variance compounds on itself. The uncertainty multiplies.
It's chaos on top of chaos.
Yeah, exactly. But Derbazi reveals a mechanism he calls the posterior averaging identity. He asks a seemingly impossible question. What is the kernel of this massive, complex, compound monthly payout law? The answer he proves is shockingly simple. The compound law actually inherits its kernel directly from the underlying counting law.
Wait, I need to stop you again because that sounds almost too good to be true.
I know it does.
You are telling me the extreme complexity of the individual claim payouts. The difference between the $50 bumper and the $500,000 medical bill doesn't ruin the math. The kernel of the total massive monthly payout only cares about the mathematical distribution of the number of claims?
The complexity of the payouts does not ruin the math, provided that the severity distribution meets one highly specific, vital condition. The summon law, which is the distribution of the individual claim payout amounts, must be what is called PF2. That stands for a Polya frequency sequence of order 2.
Okay, we cannot just drop Polya frequency sequence of order 2 and move on. We have to unpack the mechanics of PF2. What does that actually mean for the data?
In plain English, a PF2 distribution is one that is log concave on its support.
Meaning?
It means the distribution of the claim amounts has a predictable, well-behaved, structured shape. It cannot have extreme, erratic, mathematically infinite heavy tails. As long as the individual claim amounts follow a PF2 distribution, Derbazi proves that the resulting posterior kernel remains TP2, totally positive of order 2.
Total positivity. It sounds like a corporate wellness mantra. Maintain your total positivity of order 2.
It does sound like a self-help slogan. But in rigorous mathematics, TP2 means that the variables move together in a reliable, consistently stochastically increasing way. They don't suddenly inverse or rebel against each other.
So they play nice.
Right. Because the PF2 condition guarantees this total positivity, the new, massive, overwhelmingly complex compound kernel reduces to something manageable. It is simply the posterior expectation of the original counting kernel. The structural math holds perfectly. You don't need to try and calculate the kernel of the entire compound mess. You just take the expected value of the simple kernel of the claim counts, given the final total payout.
To really drive home how powerful this reduction is, Derbazi runs through Table 2 in the paper. He examines the 5 classical counting laws used universally in actuarial science: the Poisson, the geometric, the negative binomial, and the log series distributions.
And what he shows in that table is mathematically staggering. For every single one of those 5 classical counting laws, when you calculate the kernel, it isn't some spiraling messy curve. It is literally just an affine function.
And a affine function is just a straight line, correct? The
hmm
basic y mx plus by equals mx plus b that we all learned to graph in middle school algebra.
Exactly. It reduces to a straight line. Because the kernel of the underlying counting law is a perfect straight line, its monotonicity, whether the line goes up or goes down, depends entirely, 100%, on a single coefficient in the formula.
Just one number.
Just one. If that one coefficient is positive, the line goes up. If it goes up, you immediately, trivially prove the likelihood ratio ordering for a massively complex random sum of random variables actuarial model.
And this affine function revelation solves a massive, frustrating bottleneck in the existing scientific literature, doesn't it?
It absolutely shatters a bottleneck. The paper specifically references very recent work by Zia and LV from just earlier in 2024.
Okay.
They were heavily researching these compound distributions, but their math got stuck. They could only prove the weaker relative log concavity order for certain compound models. They completely failed to prove the much stronger, much more desirable likelihood ratio order for compound geometric laws with general PF2 summons.
Why did they fail?
The traditional ratios were just too complex to integrate. Derbazi's kernel approach breaks right through that exact barrier. Because he shifts the focus entirely to the simple monotonicity of the affine kernel, just looking at the slope of a straight line. The likelihood ratio comparison is delivered cleanly and effortlessly. It extends the boundaries of the statistical literature significantly.
So we've walked through the compound laws and the posterior averaging identity. Does that cover the final technical sections of the paper?
Yes, I believe we've hit all the critical mathematical pillars.
So what does this all mean? Let's zoom out and summarize this incredible journey for everyone listening. Derbazi took one of the most notoriously difficult, computationally heavy, error-prone mathematical tasks in statistics, using massive likelihood ratios to definitively prove that one complex risk profile dominates another, and he effectively bypassed the hardest parts of it.
He changed the rules of the game.
He really did. He introduced the concepts of the score and the kernel. By simply utilizing the derivative of the log density, he stripped away the noisy normalizing constants.
And the sheer versatility of the framework is what makes it a masterpiece. From clean, textbook exponential families to messy, real-world, zero-inflated factory data when machines are turned off, across invisible mathematical bridges connecting multi-parameter models, and even deep into the compounding chaos of random sums of random severity.
And it's all connected.
This single, elegant tool unlocks the entire strict hierarchy of stochastic orders. It literally reduces pages of grueling integrations to a simple visual shape analysis of a single curve.
It truly is a masterclass in finding profound simplicity on the far side of intense mathematical complexity. And as we wrap up this deep dive, I want to leave you, our listener, with a final provocative thought to mull over.
Let's hear it.
Throughout this entire discussion, we've seen how the kernel approach dramatically simplifies comparing models when we have a fixed parameter, even multiple fixed parameters, a defined set of dials we can turn, like a defect rate or an average stock return. But what if we move beyond parametric families entirely?
Oh, that is the uncharted frontier of this math.
Right. What if we aren't turning a defined dial at all? Could we use a similar functional derivative approach? Perhaps a kind of infinite dimensional kernel to establish rigorous stochastic ordering between completely non-parametric, fully data-driven distributions.
Like an AI.
Exactly. I'm thinking specifically about the shifting, opaque, millions of interconnected weights inside a deep neural network, or a massive, raw, empirical data set where the parameters are literally just the millions of data points themselves. If Derbazi can ingeniously collapse a complex likelihood ratio into a single kernel to measure actuarial risk, could we build an infinite dimensional kernel to definitively mathematically prove that one AI model's output is fundamentally safer or structurally more reliable than another's?
If a mathematician can crack the infinite dimensional extension of Derbazi's kernel, it would completely revolutionize the field of machine learning safety, providing the exact same rigorous bedrock that Derbazi has just provided for parametric statistics.
The ultimate X-ray machine for diagnostic muddy waters might just be on the verge of a massive upgrade. It is definitely something to think about the next time you are faced with comparing two incredibly complex, daunting risks. Thanks for joining us on this deep dive. Welcome to the deep dive. Today, we are looking at a stack of incredibly dense statistics, specifically a 2026 paper by Zakaria Derbazi that claims to have found a mathematical cheat code for predicting chaos.
Yeah, it is a truly fascinating problem to tackle.
It really is. I mean, if you have ever wondered how actuaries know exactly how risky your life is, or how scientists rigorously prove that one complex, unpredictable scenario is definitively more dangerous than another, well, this deep dive is for you.
Right, because we are going to unpack the ultimate mathematical shortcut today.
Exactly. Because usually when we think about math, we expect absolute, concrete precision.
Oh, absolutely. You write an equation on a chalkboard, you solve it, and there is your answer.
Yeah, it's a solid number. You can point to it.
It is very comforting. We all like a universe that we can perfectly categorize.
We really do. But the moment you step into probability, well, the chalk just shatters. You aren't looking at neat single answers anymore.
Yeah, not at all. You are looking at a landscape of random chance.
Right, you are dealing with distributions, which, are really just massive blurry clouds of likelihoods.
And comparing two blurry clouds of likelihoods is honestly one of the foundational challenges of modern statistics.
That sounds like a nightmare.
It can be. I mean, if I have one cloud that represents the risk of a hurricane hitting the East Coast under current climate models, and another cloud representing that risk with a 2-degree rise in ocean temperatures, how do I definitively prove the second cloud is larger?
Which is exactly the mission we are on today.
Right.
We are looking at this paper from Queen Mary University of London, and the title is Kernel Characterizations of Stochastic Orders Within Parametric Density Families.
Is quite a title.
It is. I know that title sounds like a wall of academic jargon, but our goal here is to extract the beautiful underlying logic of how we compare chaotic systems.
Right. We are going to skip the overwhelming algebra.
Exactly. Bypass the dense equations and keep all the real aha moments for you.
Because what Derbazi has done here is, frankly, remarkable. Historically, proving that one probability distribution dominates another requires some incredibly heavy computational lifting.
Like a brute force approach.
Exactly. It is totally brute force. But what this paper offers is a way to bypass all that heavy lifting entirely.
Just by looking at the underlying mathematical DNA of these probabilities, right?
Yes, exactly.
Okay, let's unpack this. Before we can talk about comparing these massive clouds of probability, we need to understand the basic environment this paper is operating in.
Right, the groundwork.
So Derbazi focuses on something called parametric families of probability measures. Let's establish what that means for anyone listening who doesn't spend their weekends reading statistics textbooks.
Well, think of it as standardizing the playing field.
Yeah.
To build a rigorous comparison, you first need a standardized way to define what you are actually comparing.
That makes sense.
So a parametric family is essentially a group of probability distributions that all share the exact same underlying mathematical structure.
Okay, so the core math is the same.
Yes, the formula is identical, but they have one or more adjustable dials, and those dials are what we call parameters.
Let me try to ground this with an analogy. I like to think of it like a family recipe for chili.
Oh, I like that.
Yeah, so the base recipe, the ratios of beans, tomatoes, onions, the cooking time, that is the foundational mathematical formula.
Right, the structure of the distribution.
Exactly. It is the same for every single batch of chili you make. But you have a dial on your stove or a dial on a spice rack, the spice level.
The spice level, yes.
That spice level is our parameter.
That is a highly effective way to visualize it.
Mm.
If you're trying to mathematically compare a mild chili to a 5-alarm chili, well, you don't need to analyze the tomatoes or the beans.
Because they belong to the same family.
Right, they belong to the same parametric family.
Yeah.
The only thing that has changed is that parameter setting.
And the fundamental challenge we are trying to solve is figuring out exactly how turning up that spice dial changes the overall experience of the chili.
Exactly.
Like, does turning the dial from a 2 to a 3 just slightly shift the average heat? Or does it fundamentally change the likelihood of you getting an agonizingly spicy, day-ruining bite?
And that question is the core of stochastic ordering. We need to prove mathematically how the system behaves when the dial moves.
Okay, so how do we do that?
To do that, Derbazi relies on a specific mathematical tool to measure the effect of the dial. It is called the score.
Okay, here is where we need to slow down a bit. Because the paper defines the score as the derivative of the log density with respect to the parameter.
Yes, it does.
For anyone who hasn't taken a calculus class in the last decade, That sentence is just an incredibly dense brick of math.
It is very dense, yes.
I mean, I'm following you on the chili parameters, but I have to admit some genuine confusion here. Why are we bringing calculus and logarithms into this?
Well, it's about simplifying the mechanics.
But if we just want to know if one chili is hotter than the other, why on earth do we need a derivative?
It is all about simplifying the math so it doesn't break our computers, to put it bluntly. Let's separate it into two parts, starting with the logarithm.
Okay, let's start there.
In probability, you are very often dealing with the multiplication of many, many tiny numbers. If you are trying to calculate the probability of a specific sequence of 100 coin flips, you are multiplying fractions over and over and over.
Right, half times a half times a half. It gets microscopically small very quickly.
Exactly. And mathematically, dealing with massive chains of multiplication becomes incredibly messy.
I can imagine.
In the real world, when computers try to multiply thousands of tiny fractions, they experience something called underflow.
Underflow, what does that mean?
The numbers get so small that the computer's architecture literally cannot hold them anymore. It just rounds down to zero, throws its digital hands up, and gives up.
Oh, wow. So the math just collapses under its own weight.
It does. But if you take the logarithm of a probability density, you invoke one of the most useful properties in all of mathematics. Logarithms turn multiplication into addition.
Oh, that is clever.
It is. Suddenly, instead of multiplying 1,000 tiny fractions and watching the number vanish into nothing, you were simply adding up 1,000 numbers.
Which is much easier to process.
Right, it takes a tangled multiplicative mess and flattens it out into a neat, stable additive line.
I see. So taking the logarithm is basically a structural reinforcement. It smooths out the math so we can actually work with it.
Yes, precisely.
But that only explains half of the log derivative phrase. Why are we taking the derivative of this log density with respect to the parameter?
This gets back to your chili analogy.
Mm-hmm.
A derivative is simply a measurement of sensitivity.
Okay, sensitivity.
Yes, it is a way of asking the math a very specific question. If I nudge this parameter just a microscopic amount, how drastically does the outcome change?
Oh, I get it. So if you bump your spice dial from a 2.0 to a 2.01, does the heat barely register or does the whole pot boil over?
Exactly. The score, this derivative of the log density, is the mathematical pulse of that exact sensitivity.
Okay, that makes complete sense now. We are taking the pulse of the dial. But here is where it gets really interesting, and honestly where I need you to guide us a bit.
Sure.
The paper introduces what is clearly the central idea of this entire deep dive, the kernel.
Yes, the kernel.
Derbazi defines the kernel as simply the score, but before it has been centered. It is the score minus some mathematical constant that doesn't depend on the data.
That is correct. It strips away certain mathematical constants.
So wait, if the kernel is basically just the score minus some extra baggage, why do we even need a new word for it?
That is a very fair question.
I mean, statisticians have been using something called a likelihood ratio to compare probability distributions for decades. It is the standard tool. Why not just use the likelihood ratio like everyone else? Why invent this kernel concept?
You are touching on something critical there, because understanding the failure of the likelihood ratio is really the only way to appreciate the genius of what Derbazi has built.
Oh, really?
Yes. The likelihood ratio is the traditional tool. If you want to know if distribution A is bigger or riskier than distribution B, you divide the density of A by the density of B.
Okay.
You look at the ratio, and if the ratio consistently goes up as the values get larger, you have your proof.
It sounds straightforward enough. Division isn't exactly quantum mechanics.
Conceptually, it is straightforward. Computationally, it is a nightmare.
A nightmare. How so?
When you divide two complex probability distributions, the resulting fraction can become an absolute monster. You aren't just dividing simple numbers, you are dividing normalizing constants, massive factorials, complex exponentiations.
Oh, wow.
The algebra becomes so tangled that trying to prove anything about the ratio is grueling.
It's like trying to figure out which of two cars is faster by smashing them into each other at high speed and trying to weigh the wreckage. There are just too many moving parts, too much twisted metal.
I like the wreckage analogy, but let's refine it a bit. Imagine instead that you are a botanist trying to compare two massive oak trees to see which one is structurally stronger.
Okay, two oak trees.
The likelihood ratio approach is like trying to compare the two trees by individually measuring and dividing the weight of every single leaf, every branch, and every piece of bark.
That sounds impossible.
It is an overwhelming amount of raw data. And a lot of it, like the leaves, doesn't actually tell you much about the core structural strength.
You're just drowning in noise.
Drowning in noise.
Yeah.
But Derbazi's kernel bypasses the leaves entirely. By taking the log derivative, he mathematically strips away all those normalizing constants.
The structural noise.
Exactly, all the structural noise of the distribution that doesn't actually interact with the data point you are analyzing. The kernel isolates only the genetic code of the tree.
Just the genetic code.
Yes, it looks purely at the factors that change when the parameter dial interacts with the raw data. It is the bare functional DNA of the probability distribution.
And because it is so stripped down, it is infinitely simpler to work with.
Infinitely simple.
So it's an extreme distillation process. We start with the messy likelihood ratio, apply the logarithm to stabilize it, take the derivative to measure its sensitivity, and then strip away the constants to find its pure DNA.
That is a perfect summary.
But to keep the math honest, before we can actually use this distilled kernel to sort anything, Derbazi lays out a set of ground rules, right?
Yes, to ensure the environment is structurally sound.
The paper describes a condition involving differentiation under the integral and something called a majorant condition.
Right, assumption 2.1.
We promised you listening that we would keep the heavy math to a minimum, but we have to understand the boundaries of the playground. What is the conceptual purpose behind these ground rules?
The simplest way to think about these rules is to view them as the safety rails on a roller coaster.
Okay, safety rails.
If we are going to use derivatives to measure how fast things are changing, how sensitive the probability is to our parameter dial, we have to mathematically guarantee that the rate of change doesn't suddenly spike to absolute infinity.
Because if the sensitivity goes to infinity, the math literally breaks. You get a divide by zero type of catastrophic failure.
Precisely. If the function isn't smooth, if it has sudden infinite cliffs, a derivative becomes meaningless. You cannot measure the slope of a vertical wall.
Right, that makes sense.
What Derbazi is doing with these specific mathematical conditions is rigorously proving that his environment is safe. He is mathematically guaranteeing that the functions are smooth enough and bounded enough that when we calculate the kernel, we will get a reliable, finite answer every single time.
So it's the bedrock.
Yes, it is the bedrock that ensures the magic in the rest of the paper actually works.
Okay, so we have our safe environment and we have our mathematical magnifying glass, the kernel. Now, what do we actually point it at?
This is where we get to the core framework of the paper.
Right. Derbazi takes this newly forged tool, the kernel, and applies it to the four distinct ways that statisticians rank probabilities. This is essentially the sorting hat of the deep dive.
And these four pillars of stochastic ordering are the foundation of risk analysis.
Let's walk through them, starting with the most intuitive one. It is called the usual stochastic order.
The usual stochastic order is exactly what it sounds like. It's the broadest, most common way to say one thing is bigger than another.
Give me an example.
If you have two random variables, let's say we're looking at the heights of adults in two different cities, City A and City B. If we say City B is stochastically larger in the usual sense, it just means that if you pick a random person from each city, City B is consistently more likely to produce the taller person.
So the entire cumulative probability curve is just shifted to the right. Generally speaking, the numbers from the second cloud are just larger than the numbers from the first cloud.
Exactly. It doesn't mean every single person in City B is taller than every person in City A, but the overall mass of the probability favors the larger values.
Simple enough. But the second way to rank things is a bit more nuanced. It's called the hazard rate order.
Yes, the hazard rate order.
When I hear hazard rate, I think of insurance premiums. What does it mean to compare the hazard rates of two chaotic systems?
A hazard rate introduces the concept of time or conditionality. It doesn't just look at the overall outcome, it looks at the conditional probability of an event happening right now, given that it hasn't happened yet.
Okay.
It is the backbone of survival analysis and reliability engineering.
Let's use a real-world example. Say we are comparing the lifespans of two different light bulbs. We have an old-school incandescent bulb and a modern LED bulb.
Okay.
The hazard rate isn't just asking which bulb lasts longer on average, right?
No, it asks a much more specific question. It asks, given that both bulbs have miraculously survived for exactly 1 year, what are the odds of them burning out in the very next minute?
Wow, that is specific.
And then given that they both survive for 2 years, what are the odds of them failing in the next minute?
So it's constantly recalculating the risk based on the fact that the object has survived up to this point. It is looking at the immediate present tense danger.
That is a great way to phrase it. The immediate present tense danger. If the incandescent bulb consistently has a higher immediate risk of burning out than the LED at every single point in time, assuming they've both survived to that point, then it is ordered higher in the hazard rate sense.
That is a strict
It
comparison.
is a much stricter comparison than the usual stochastic order. You aren't just saying LEDs last longer. You are mathematically proving they are fundamentally more robust at every single milestone of their existence.
Okay, so that's the second way we sort things. The third pillar is the likelihood ratio order.
The likelihood ratio order, yes.
Now, we talked earlier about how calculating likelihood ratios can create monstrous, tangled fractions. But as a conceptual framework, what does this specific order mean?
The likelihood ratio order is the gold standard. It is the strictest of the four pillars. Conceptually, it requires that the ratio of the two probability densities is entirely non-increasing across the whole spectrum.
Let's translate that into plain English.
In practical terms, it means the mathematical evidence heavily and consistently shifts in favor of the larger distribution as the values get higher.
Okay, I follow.
The larger the data point you are looking at, the more aggressively the math points to the second distribution. It is so strict that if you can prove distribution B dominates distribution A in the likelihood ratio order, the math automatically guarantees that it also dominates in the hazard rate order and the usual stochastic order.
It trickles all the way down.
Triples all the way down.
So it's the ultimate proof of dominance. If you win the likelihood ratio, you win everything else by default.
You do, but because it is so strict, it is historically the most difficult to prove.
Which brings us to the fourth and final pillar, relative log concavity. Honestly, just saying those words makes me feel like I need a nap. What does it mean?
It sounds intimidating, I know, but it is really just a question of geometry. It is about the shape of the distributions.
The shape.
Yes. It asks if the fundamental curve of the likelihood ratio between the two distributions is concave.
Meaning it curves downwards like an upside-down bowl.
Exactly, like a bowl.
Yeah.
It tells us about how the spread or the tails of the probabilities behave relative to one another. It's a way of understanding how the extreme outliers of the two clouds compare.
So we have these four pillars, four different highly complex ways to definitively prove that one random scenario dominates another.
Right.
And this is where Derbazi drops the absolute mic. He reveals a unified set of criteria using that distilled bare-bones kernel we talked about earlier.
Yes, Theorem 3.5 in the paper.
He proves that you don't need to do the grueling, monstrous algebra for all four of these orders separately. You don't need to weigh all the leaves on the tree. You just look at the shape of the kernel.
This is where the paper moves from being an interesting concept to a profound mathematical achievement. It's breathtaking in its elegance.
It really is.
Derbazi proves that you can completely determine the stochastic ordering just by looking at the geometry of this one simple line.
Let's break down how this magic trick actually works. If we want to prove that gold standard, the strict likelihood ratio order, what shape does the kernel need to be?
It just needs to be monotone, meaning the line strictly goes up, strictly goes down across the entire graph. If the kernel is purely monotone, it is mathematically guaranteed that the likelihood ratio order holds true.
Wait, that's it. Just is the line pointing up?
That is literally it. But let's explore why that works, because it's important to understand the mechanism here.
Please do.
Remember that the kernel is basically the derivative of the logarithm. It is the measurement of sensitivity. If the kernel is always going up, if it is monotonically increasing, it means that as your data points get larger, the parameter dial has a stronger and stronger positive effect.
So the larger the value, the harder the parameter pushes the probability upward.
Exactly. The rate of change heavily favors the extreme values. So, purely by the logic of calculus, a perfectly upward-sloping kernel guarantees that the second distribution fundamentally dominates the first across the board.
That is incredibly satisfying. And what about the relative log concavity, the upside-down bowl shape?
Derbazi shows that if the kernel itself is concave, if the line of the kernel curves downward as it moves to the right, you immediately guarantee relative log concavity between the two distributions.
So again, it maps perfectly.
Perfectly. The geometry of the kernel directly dictates the complex relationship between the probability clouds.
Okay, but what if we want to prove the hazard rate or the usual stochastic order? What shape does the kernel need to be for those?
For those, he introduces a concept called tail conditional mean inequalities.
Tail conditional mean inequalities. That is a mouthful.
It sounds like a mouthful, but the visual is actually quite straightforward. Instead of just looking at the overall shape of the line, you pick a specific point on the graph.
Okay.
Then, you calculate the average value of the kernel for everything to the right of that point. the entire tail of the distribution.
So you are comparing the kernel's value right now to its average value in the future.
Precisely. If the kernel's value at your chosen point is consistently smaller than the average value of the tail ahead of it, you automatically get the hazard rate order.
Wow.
It's a way of proving that the momentum or the gravity of the probability is constantly pulling toward the larger values.
So what does this all mean for someone actually doing the math? Let's ground this.
Good idea.
In the paper, Derbazi provides a catalog where he applies this kernel framework to classic famous distributions. Let's look at the Poisson distribution.
A classic.
For you listening, the Poisson distribution is the math used to predict the frequency of isolated events. It's how call centers predict how many calls they will get in an hour, or how astronomers predict how many meteors will hit the Earth in a year.
It is one of the most foundational distributions in all of applied statistics.
Right, and normally if you wanted to prove the likelihood ratio for two Poisson distributions, say, comparing a busy call center to a quiet one, you would have to divide massive factorials. You would be writing out huge, tangled fractions.
Yes, lots of factorial division.
But with Derbazi's method.
With Derbazi's method, you find the kernel. And the kernel for a power series like the Poisson distribution turns out to just be a straight upward sloping line.
Just a straight line.
It's what mathematicians call an affine function. It is literally just the data point divided by the parameter.
A completely straight line.
A completely straight line. And because a straight line is perfectly monotone, it never dips, it never wobbles, Derbazi's framework instantly guarantees the likelihood ratio order.
No dividing factorials, no complex algebra.
No.
You look at the kernel, you see a straight line, and you are done. The proof is finished.
It takes a dense, terrifying algebraic forest and completely clears it out, leaving behind a single straight path.
Let's do another one. Look at the gamma distribution.
Okay, the gamma distribution.
The gamma distribution is used heavily in queuing theory to model wait times. It's the math you use to predict how long you will be standing in line at the grocery store, or how long until the next bus arrives. The parameter we care about here is the rate of the buses.
If you apply the kernel extraction to the gamma rate parameter, the result isn't some wild calculus equation. All the normalizing constants strip away, and the kernel melts down to literally just negative x.
Negative x, that is a 45-degree downward sloping line.
Which, again, is perfectly monotone. It perfectly and instantly orders the probabilities. It is a profound simplification of standard statistical theory. It bypasses decades of computational struggle.
I love when complexity just collapses into something so visibly simple. It genuinely feels like finding a cheat code for reality.
It really does.
But of course, the real world is rarely that clean. It's intensely satisfying when a kernel is a perfectly straight line, but real-world data is notoriously messy.
Very messy.
What happens when the kernel misbehaves? What if it goes up for a bit and then dips down? Do Derbazi's elegant rules just fall apart?
That is the ultimate test of any mathematical framework.
Yeah.
It is easy to make rules for perfect systems. It is much harder to make rules for broken ones.
Right.
As you noted, what if a kernel is neither perfectly monotone nor perfectly concave across its entire graph?
Under traditional methods, if the likelihood ratio isn't perfectly monotone, you simply cannot prove a strict likelihood ratio order. The math fails, and statisticians traditionally just throw up their hands and say the distributions cannot be ordered.
They do. They walk away from the problem. But Derbazi doesn't throw up his hands.
Right.
This is where his tail conditional inequalities really flex their muscles. He realizes that he needs a new rule for messy data, and he introduces a brilliant rescue operation called the superlevel set criterion.
Okay, let's unpack this. Superlevel set. What are we visualizing here? How does this rescue messy data?
Imagine graphing the score of a distribution, which remember is just the centered version of the kernel. You have an x and y axis, and the zero line runs right through the middle.
Got it.
The superlevel set is simply the portion of your graph that sits above the zero line. It is the physical area where the score is positive.
So it's everything above sea level.
Exactly. Everything above sea level. Derbazi proves that even if the kernel wobbles, even if it's not perfectly monotonic and goes up and down, you can still order the distribution if the superlevel set behaves in a specific way.
How so?
As long as that positive area forms a solid, unbroken initial chunk above sea level and then drops below sea level into negative territory without ever bouncing back up, the tail conditional inequalities still hold true.
Wow, so even if the gold standard likelihood ratio order completely fails because the line isn't perfectly straight, This superlevel set rule swoops in.
It does.
It mathematically guarantees that the hazard rate order and the usual stochastic order still survive.
Yes, it proves that a distribution can still be definitively larger or riskier overall, even if the strict local ratio gets a little tangled in the middle. It allows statisticians to maintain rigorous proofs even when the data isn't perfectly behaved.
Let's look at one of the fascinating examples he uses in the paper to prove this, because it highlights just how clever this workaround is. He applies it to the half-student distribution.
Yes, the student distribution is incredibly common in statistics, particularly when you are dealing with very small sample sizes.
But its kernel is notoriously uncooperative.
Very much so. On a full graph, the student kernel looks like a symmetric bell or a bump. It starts low, goes up to a peak, and comes back down.
So it's a hill. It's completely non-monotone because it goes up and down. And it's not concave either because the tails of the hill curve upwards before they flatten out.
Right.
So the unified rule we talked about earlier completely fails here.
It fails completely. The strict rules are broken. But Derbazi says, what if we chop that distribution in half? Just look at the positive side, the half-student distribution.
Yeah, okay.
If we only look at the right side of the graph, we're essentially starting at the peak of the hill and sliding down.
But it still has those upward curving tails at the bottom, so it's still not concave.
Right, but this is where the superlevel set rule saves the day. By chopping it in half, the kernel starts high above sea level, drops down across the zero line, and stays below sea level forever.
Oh, I see.
It never bounces back up.
Good.
The superlevel set is a perfect, unbroken initial chunk. And because of that, Derbazi mathematically proves that the hazard rate and stochastic orders are absolutely guaranteed.
It really is like finding a loophole in the laws of probability. You take a shape that shouldn't be allowed to work, slice it in half, look at what's above sea level, and suddenly you have a rigorous mathematical proof.
It is brilliant.
And my absolute favorite example of this messy data rescue operation is what he calls zero inflated laws. This is so incredibly applicable to real life.
It is probably the most practical application in the entire paper.
Let's use an analogy to explain what zero inflation actually is, because the math gets heavy fast. Imagine a massive manufacturing factory. At the end of the assembly line, there is a quality assurance inspector whose only job is counting minor manufacturing errors every hour.
Okay, a factory inspector.
Under normal circumstances, the number of errors follows a beautiful, predictable Poisson distribution. Maybe there's an average of 2 tiny errors an hour. It forms a nice, predictable mathematical curve.
That is a standard, well-behaved parametric family.
Right. But what if the inspector is severely overworked, and occasionally they just fall asleep at their desk for a solid hour?
Oh, no.
The assembly line keeps moving, but no one is watching. The inspector wakes up, panics, and quickly writes down 0 errors on the clipboard to cover their tracks.
I can see where this is going.
Suddenly, your real-world data doesn't look like a nice curve anymore. You have this unnatural, massive spike of 0 errors recorded in your data set. That massive spike is a zero inflated law.
And mathematically, that sleepy inspector wreaks absolute havoc on traditional ordering.
Yeah.
The massive spike of fake zeros completely corrupts the data at the origin point.
Right.
The likelihood ratio between a normal functional factory and the sleepy inspector factory will wildly jump around to the 0 mark. It is mathematically chaotic. If you use traditional methods, the likelihood ratio order fails instantly. You cannot strictly compare them.
Because the math assumes the zeros are real and tries to account for this massive, impossible anomaly.
Exactly. But Derbazi's framework survives the sleepy inspector
How does looking at a kernel fix corrupted data?
because he relies on those tail conditional mean inequalities we discussed. Remember, the tail conditional rule looks at the average of the distribution ahead of a certain point.
Yes, looking at the tail.
Derbazi proves mathematically that even though the 0 mark is completely chaotic and corrupted, if you look at the conditional expectation of the tail, meaning if you mathematically ignore the spike of zeros and only look at the hours where errors were actually recorded, the fundamental relationship between the two factories remains perfectly intact.
So the kernel naturally isolates the true behavior of the system, bypassing the anomaly.
It does. Amazingly, the hazard rate and usual stochastic orders survive the 0 inflation. You can still definitively mathematically prove which factory is fundamentally producing more errors overall, despite the fact that the 0 data is completely corrupted.
That is just incredibly powerful. It means this framework isn't just theoretical math meant for pristine chalkboards. It is a rugged tool built for the ugly, zero-inflated reality of messy data. It works in the real world,
It absolutely does.
which is a perfect transition into the final major concept of the paper. Because up to this point, we've basically mastered how to turn one parameter dial, the spice level, inside a single, simple family of distributions.
Yes, we've stayed within families.
But Derbazi decides to push this kernel to its absolute limits. He asks a much harder question. What if we turn multiple dials at once? Or what if we want to compare two totally different recipes entirely?
This is where the paper elevates from being a very useful statistical tool to becoming a comprehensive mathematical framework. He tackles joint parameter paths and interpolation.
Let's break that down. Interpolation paths.
Suppose you want to compare a beta binomial distribution directly to a standard binomial distribution. These do not belong to the same simple one-parameter family. They are structurally different.
Going back to our food analogy, it's like trying to compare a pot of chili directly to a pot of curry.
Good analogy.
How do you mathematically prove one is definitively spicier when the base ingredients, the cooking methods, and the entire structure of the recipe are different?
Derbazi solves this by constructing a mathematical path between them, an interpolation. He essentially creates a sliding scale that slowly morphs the mathematical structure of the beta binomial distribution into the binomial distribution.
Okay, a sliding scale.
And the kernel, in this scenario, adapts. It becomes the log factor ratio between the two laws as you move along that morphing path.
Oh, this is exactly like audio mixing. Imagine you are a DJ in a club. You have track A playing on the left turntable, and you want to seamlessly transition to track B on the right turntable.
Yeah.
Use a crossfader. You slowly fade out the volume of track A while simultaneously fading in the volume of track B. Derbazi is basically saying, by looking at the mathematical rate of that crossfade, the derivative of the interpolation path, you can definitively prove which song is mathematically louder overall.
That is an exceptionally accurate analogy. The kernel in this scenario captures the exact gradient of that crossfade.
The gradient.
If the path kernel is non-decreasing as you slide the fader from track A to track B, then you have successfully proven the likelihood ratio order between two completely different distributions. It bridges the gap between disparate families, allowing you to mathematically order things that previously seemed entirely incompatible.
It's stunning. But he doesn't stop with crossfading. He takes us to the absolute deep end of probability theory. Compound laws. The Matryoshka dolls of statistics.
The nested dolls, exactly. A compound law is a random sum of random variables.
To put it in tabletop gaming terms, for anyone who plays Dungeons & Dragons, it's not just rolling a 20-sided die to see how much damage you do.
No, it is much more complex.
A compound law is rolling a 6-sided die, and whatever number comes up on that die, that is how many 8-sided dice you get to roll for the actual damage. The number of events is completely random, and the outcome of every single one of those events is also completely random. It is pure chaos nested inside of chaos.
And trying to establish a strict stochastic order for compound distributions using traditional likelihood ratios is notoriously, punishingly difficult.
I bet.
Because the equations become massive convolutions. You are multiplying variables of variables. The math balloons out of control almost instantly.
But Derbazi applies the kernel framework here as well.
Mm-hmm.
He introduces a concept he calls the posterior averaging identity.
Yes.
Okay, I need your help unpacking this one. Posterior averaging. What is the mechanism here?
It sounds incredibly complex, but the underlying logic is beautiful. He proves that the incredibly complex compound law, the giant outer Matryoshka doll, simply inherits its kernel from the underlying counting law, the smallest doll deep inside.
Wait, really? It just inherits it?
It does. If you know the kernel of the very first die roll, the one that determines how many events are going to happen, you can mathematically determine the stochastic order of the entire compounding, cascading chain of events.
So you don't have to map out every possible combination of the 8-sided dice?
No, you do not.
You don't have to calculate every possible sprawling timeline of damage. You just look at the kernel of the 6-sided die that triggered them in the first place.
Exactly. He proves that the compound kernel is simply the expected value, the posterior average, of the counting kernel, given the final sum. He highlights the Poisson binomial law as a specific example in the paper.
Okay.
As long as the underlying distribution, the thing being added up, meets a specific shape criteria, the math works.
The paper mentions it has to be log concave, right? It has to have that smooth, downward curving bowl shape?
Correct. As long as it has that shape, the conditional expectation behaves perfectly. You can prove likelihood ratio ordering for massive chaotic compound variables just by looking at the slope of the kernel of the initial counting distribution.
That is wild.
It takes a problem that would normally require a supercomputer to simulate thousands of times and reduces it to a handful of elegant, straightforward algebraic steps.
It truly is breathtaking. So let's take a breath ourselves and review the massive journey we have just been on. We started with this dense, terrifying concept of comparing chaotic probabilities using a log derivative score.
Yes, we did.
But we saw how Derbazi stripped that heavy math down to its raw, pure DNA, creating the kernel.
A mathematical magnifying glass.
And by simply looking at the geometry of that kernel, is it a straight line pointing up? Does it curve downward? Does its superlevel set stay above sea level? We can flawlessly, rigorously rank chaotic distributions.
We can prove mathematically which one is riskier, which one is larger, and which one dominates the other, without ever dealing with the monstrous tangled fractions of the traditional likelihood ratio.
And we didn't just stay in perfect, pristine theoretical environments. We applied this kernel to the messy reality of zero-inflated data where sleepy factory workers mess up the counts.
Right, the real world.
We used cross-fading interpolation to compare totally different families of probability, and we unpacked the chaotic matryoshka dolls of nested compound random variables.
It is a sweeping, incredibly comprehensive framework that changes how we analyze risk.
Which brings me to the most important question for you listening right now. Why should you care about this? Why did we just spend an hour deep diving into the kernel characterizations of stochastic orders?
It is a fair question to ask.
We care because we live in a world that is absolutely drowning in data. We are relying on actuarial risk modeling to predict the next century of climate insurance. We are relying on machine learning algorithms that are trading on unfathomable amounts of chaotic real-world inputs.
Exactly.
In that world, finding a mathematical shortcut that bypasses computationally heavy operations isn't just a neat academic trick, it is vital. It is like finding a hidden wormhole in the fabric of statistics.
Wormhole, yeah.
It saves massive amounts of computing time, it prevents catastrophic errors like underflow, and above all, it reveals the underlying hidden elegance of random chance.
It reminds us that even inside the muddy, unpredictable waters of probability, there is an architecture. There is a deep, fundamental structure if you know how to look for it.
There is structure, but I want to leave you with a final provocative thought. Something to chew on that isn't explicitly solved in Derbazi's paper, but pushes the boundary of what we've learned today.
Okay, let's hear it.
This entire framework, this beautiful, elegant sorting hat that Derbazi built, relies entirely on the ability to take a derivative. You have to be able to smoothly turn that parameter dial and measure the sensitivity.
You use a smooth, continuous curve to find a tangent line. Without a smooth curve, the derivative doesn't exist.
Right. But what happens if we move into the realm of quantum mechanics? Or what if we look at discrete, non-differentiable network states, like the instantaneous, jagged snapping of a power grid during a blackout?
That is a very different environment.
You cannot take a standard derivative of a quantum jump. It's not smooth, it's instant. So my question is, could there be a fractional kernel? Could there be a discrete analog of a score that unlocks this exact same beautiful stochastic ordering for completely chaotic, non-smooth, non-differentiable systems?
That is the next great mathematical frontier. If someone can bridge the discrete gap with the same elegance Derbazi brought to parametric densities, well, it would rewrite the textbook all over again.
It's the next muddy water waiting to be cleared. Thank you so much for joining us on this deep dive. We started by looking for precision in the chaos of probability, and thanks to the kernel, I think we found a piece of that solid chalkboard again. Stay insanely curious, keep looking for those underlying patterns, and we'll catch you on the next deep dive. Welcome to this deep dive. When most of us think about probability, we just picture the chaos of chance, right?
Right, like a roulette wheel spinning or maybe a coin flipping through the air.
Exactly. We tend to think of it as the mathematics of the unknown. But if you talk to a theoretical statistician or a reliability engineer, they don't just care about chance.
No, not at all. They care fundamentally about order.
Right. They want to ask, how do we mathematically prove that one chaotic system is inherently riskier or, larger than another?
It's like having a giant mixing board in front of you. Every dial controls the underlying fabric of a possible reality.
Yeah, like the failure rate of airplane engines or the spread of a virus. And if you turn one of those dials just a fraction, how does the shape of that reality actually change?
And more importantly, how do you prove it without calculating every single outcome from scratch?
Yeah.
That's the core issue.
Which brings us to our mission today. We're exploring a masterclass and answering that exact question, looking at a unified mathematical shortcut.
Yeah, we're unpacking a May 2026 paper by Zakaria Derbazi titled Kernel Characterizations of Stochastic Orders Within Parametric Density Families.
And just so you, the listener, are aware, we are officially activating the unabridged protocol for this deep dive.
That means we are leaving absolutely no stone unturned. We're going strictly linearly, start to finish.
Right, explaining the why behind every single mathematical concept. So let's do our first completeness check. Are the mission parameters for the intro clear?
I think we've thoroughly unpacked the setup. Let's proceed to the title and abstract.
Perfect. So looking at the title, Kernel Characterizations of Stochastic Orders Within Parametric Density Families. What exactly is a parametric density family?
Well, think of it as a family of curves shaped by a dial, like
Oh,
a standard bell curve where one dial controls the mean and another controls the variance.
okay, so the dials are the parameters, and the abstract mentions four specific orders: likelihood ratio, hazard rate, usual stochastic, and relative log concavity. Why these four?
They essentially form a hierarchy of strictness. They are the heavyweights for proving one distribution is definitively larger or riskier than another.
Got it. And the paper introduces this idea of a score and a kernel. Can we break down those definitions linearly before we move on?
Sure, the score is basically the derivative of the log density, and a kernel is just that score, but up to an additive term. We'll dig into the heavy math of that shortly.
Sounds good. So that covers the title and the abstract. Have we missed any nuances there?
I don't think so. I think we've thoroughly unpacked it. Let's proceed to the introduction.
Okay, jumping into the first 5 paragraphs of the intro. The author says the kernel is often simpler to analyze than the likelihood ratio.
Right, which is a massive claim.
But wait, why? I mean, why is taking a derivative of a log density mathematically cheaper than just analyzing a ratio?
Well, think about the mechanics. A ratio of two different parameters requires you to track two completely different moving parts.
Like carrying around two different universes of math at the same time?
Exactly.
Yep.
But a kernel, via a derivative, it isolates the rate of change at a single parameter point.
Hmm.
It's just one localized calculation.
Oh, wow. Okay, I see how that cuts down the baggage. And the intro outlines 5 main contributions, right?
Yeah, proceeding linearly, they are criteria for the orders, the superlevel set hypothesis, joint parameter paths, compound construction, and finally a catalog of examples.
We're going to hit every single one of those, so that covers the introduction. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2, the notation and preliminaries.
All right, section 2.1, conventions. And right out of the gate, the paper hits us with some heavy foundations. It says probability measures are dominated by a sigma finite measure.
Yeah, that requires a foundational digression. We need to talk about measure theory.
Please, because to anyone who hasn't taken graduate level real analysis, that just sounds like alien language. What is a sigma finite measure?
So, think of a measure as a mathematically rigorous way to assign a weight or a volume to a set of things.
Okay, like measuring physical space.
Sort of. And sigma finite is a safety valve. If you're measuring an infinite universe, the math can easily blow up into unmanageable infinities.
Right, which breaks calculus.
Exactly. So sigma finite just means that even if the whole space is infinite, you can always slice it up into a countable number of smaller, finite chunks.
Like a measuring tape that goes on forever, but you can break it down into 1-inch finite segments.
That's a great analogy. It keeps the math grounded.
Okay, but what about radon-Nikodym derivatives? Why do we need that instead of just saying probability densities?
Well, the author wants a single, unified framework. In statistics, you have smooth, continuous curves, and you have discrete dots, like rolling dice.
And usually you use integrals for curves and addition for dots, right?
Right, but a radon-Nikodym derivative acts like a universal adapter. It allows the author to use one symbol to represent both the continuous density and the discrete mass.
That is incredibly efficient. Okay, we need to activate the perfect pronunciation protocol for some foundational equations here. Let's start with the survival function.
The survival function is dApx. Fr sub p of x is defined as the measure p of the intersection of the interval x to infinity and the space E.
Got it. And the hazard rate.
The hazard rate is dpx. fpx, ftx, ftbt of x is defined as f sub p of x divided by f bar sub p of x.
And we also have equation 1, the likelihood ratio.
Right, the likelihood ratio is bp, x dq drx, is defined as the radon-Nikodym derivative of p with respect to rho at x divided by the derivative of q with respect to rho at x.
Okay, that covers the conventions in 2.1. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to assumption 2.1.
All right, assumption 2.1 is all about differentiation under the integral sign. And it mentions the Leibniz rule.
Yeah.
Why is this vital?
Because in calculus, you can't always just swap an integral sign and a derivative sign. If your space goes to infinity, doing that might cause the equation to explode.
So how do we guarantee we can safely swap them?
We need a safeguard. The paper explicitly assumes there is a majorant function, which we'll call m, in the space L1.
Wait, what does a majorant function actually do?
Think of it as a ceiling. It guarantees that the rate of change of our probability density is capped. No single point can suddenly grow at an infinite speed.
Ah, so because there's a finite ceiling, we can slide the derivative inside the integral without breaking the universe.
Precisely. It invokes the dominated convergence theorem to make everything mathematically legal.
Brilliant. That covers assumption 2.1. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 2.2, shape notions and stochastic orders.
Okay, moving linearly, we hit definition 2.2. This defines log concavity, PF2, and TP2. Let's start with log concavity.
Log concavity is basically checking if the natural log of a sequence forms a concave shape.
I always picture that like a hill that gets steeper as you climb it, right?
Right.
The second derivative is negative.
Yes. Mathematically, for a sequence A, it means the forward difference is negative. Let's use the protocol. The condition is delta 2 log Ashade to 7. The second forward difference of the natural log of k is less than or equal to 0.
Awesome. And what about PF2 and TP2?
PF2 stands for Pullier frequency sequence of order 2, and TP2 is totally positive of order 2. They are essentially exansed ways of saying the variables have a strong positive dependence. They move together.
Okay, we will definitely need that later. And then we hit definition 2.3. This formally defines the four orders we talked about in the intro.
Right. The usual stochastic, hazard rate, likelihood ratio, and relative log concavity orders.
And just to reiterate, the hierarchy likelihood ratio is the absolute strictest, right?
Yes. If you have likelihood ratio, it guarantees hazard rate, which in turn guarantees usual stochastic. It's a cascade.
Okay, that covers section 2.2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3, kernel criteria and compound laws.
This is where things get really exciting. We are finally defining the score and the kernel. Let's hit the pronunciation protocol for equation 2.
The score is C do x. Partial nu of x is defined as the partial derivative with respect to nu of the natural log of f sub nu of x.
And then equation 3 for the kernel.
The kernel is in j k sub nu of x minus the integral over j of k sub nu of y with respect to p sub nu of y.
Okay, I have to ask the big why question here. Why do we center the kernel by subtracting that integral?
Because that integral is just an annoying constant that makes the score balance out to exactly 0.
But why do we want to strip it away?
Because shifting a function up or down by a constant doesn't change its shape. If a hill slopes upward and you lower the whole hill by 50 feet, it still slopes upward.
Oh man, so we can just completely ignore all those ugly normalizing constants in the original math.
Exactly. The kernel is just the score stripped down to its bare parameter-dependent bones.
That is incredibly elegant. So that covers the definitions of the score and kernel. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.1.
All right, section 3.1 gives us density, survival, and hazard identities. Proceeding linearly, we hit proposition 3.3.
Yes, and this leads right into a crucial equation. Let's use the protocol for equation 5.
Go for it.
The integral derivative identity is partial nu, dp nu, dp nu, dp nu, dp nu, the partial derivative with respect to nu of the natural log of the integral over j of u with respect to p sub nu equals the integral over j of s sub nu with respect to p sub nu superscript u, which equals the integral over j of k sub nu with respect to p sub nu superscript u minus the integral over j of k sub nu with respect to p sub nu.
That is a mouthful. But it basically establishes how the derivative interacts with expected values. And then we hit lemma 3.4.
Right. Lemma 3.4 breaks this down line by line into equations 6, 7, and 8, applying that identity specifically to survival and hazard functions.
It's just laying the groundwork for the main theorem. That covers section 3.1. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.2, comparing laws and parametric families.
Finally, theorem 3.5. This is the core engine of the entire paper. It makes 4 massive assertions.
Assertion 1. Likelihood ratio order holds if and only if the kernel is non-decreasing.
Assertion 2. Relative log concavity holds if and only if the kernel is concave.
Assertion 3. Usual stochastic order holds if the conditional tail expectation is greater than or equal to the base expectation.
And assertion 4. Hazard rate order holds if the kernel is less than or equal to the conditional tail expectation.
Exactly. It maps the geometry of the kernel directly to the macro behavior of the probability.
Now, I want to push back on the proof for the first assertion. How does he actually prove that a non-decreasing kernel is strictly necessary for the likelihood ratio order?
He uses a masterpiece of logical deduction proof by contradiction. He assumes the likelihood ratio order is true, but that the kernel is flawed and has a dip in it.
Okay, so as you move left to right, the kernel curve goes down slightly.
Right, and since the kernel is just a shifted score, it means the score dips too. The score at point by 1 is higher than the score at a later point by 2.
Wait, but the score is just a snapshot at one exact dial setting. What happens when we physically turn the dial?
Because of the continuous scaffolding we built earlier, that dip can't just teleport away. It has to persist over a tiny window as we turn the dial.
Okay, I'm following.
And if we integrate that score over that tiny window to find the total change, we get the log likelihood ratio.
Oh. And because the score at by 1 was stubbornly higher than by 2, the integral at by 1 must be higher than by 2.
Exactly, which means the log likelihood ratio goes down, which completely breaks our starting assumption. The contradiction snaps the trap shut.
That is wild. A microscopic dip shatters the macroscopic reality. So the kernel must be non-decreasing. That covers theorem 3.5. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.3, moving beyond monotone and concave kernels.
Okay, so theorem 3.5 is great for perfect non-decreasing lines, but real-world math gets ugly. What happens when the kernel is wavy?
Well, if the kernel goes down, the likelihood ratio order is instantly dead. But proposition 3.7 gives us a way to salvage the other orders using the super level set hypothesis.
The super level set hypothesis. It sounds like a video game term. What does it actually mean?
Remember that a true score function must balance out to 0. It has to cross the 0 line like a seesaw.
Right. Positive on one side, negative on the other.
The super level set hypothesis just asks, does the score start positive and cross the 0 line exactly once?
And if it only crosses once, even if it's wavy, the usual stochastic order is preserved.
Yes, because it means mass is cleanly shifting from one side of the distribution to the other without sloshing back and forth.
That's incredibly practical, and corollaries 3.8 and 3.9 give us shortcuts for that, right?
Yeah, they basically say if the kernel is concave, you just have to check the starting edge. If it starts positive, the geometry guarantees it will only cross 0 once.
A literal cheat code for engineers. That covers section 3.3. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 3.4, compound law kernels.
Compound laws. Definition 3.0 Marrow and equation 12. These are notoriously terrifying to calculate.
Absolutely. A compound law is when you have a random number of random variables.
Like an insurance company predicting total payouts. You don't know how many crashes there will be, and you don't know how much each crash will cost.
Exactly. It's a fractal nightmare of convolution. But Derbazi solves it using posterior Bayesian averaging. Let's look at equation 13.
Okay, activating protocol.
The compound score is summon. Sto is k, S sub nu of k is defined as the partial derivative with respect to nu of the natural log of f sub nu of k, which equals the expected value of gamma sub nu of n, given x equals k.
Let me make sure I'm wrapping my head around that. He's saying we don't have to differentiate the massive convolution.
Nope. You just take the simple score of the underlying counting law, like the number of crashes, and find its expected value, conditioned on the total payout.
It's like backward-looking Bayesian inference. He just bypasses the convolution entirely. That covers section 3.4. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 4, the applications.
Putting the theory into practice. Section 4.1 gives us Table 1, which lists ordering in parametric density families.
Right. It categorizes parameters into natural, power, shape, and location.
Going back to our soundboard analogy, the scale knob stretches the probability out, and the location knob pans it left or right.
Exactly. It's a catalog of how different dials affect different families.
Nice and straightforward. That covers section 4.1. Have we missed any nuances?
I think we thoroughly unpacked it. Let's proceed to section 4.2.
Okay, example 4.3. The half-student distribution. Why are we looking at half of a distribution?
Because the standard student key distribution is a rebel. When you change its dial, the score crosses the zero line multiple times.
So it completely fails the super-level set test we just talked about.
Right. But if you chop it in half at zero and only look at the positive side, a student, it fixes the math. Let's state the derivative.
Okay, protocol active.
The half-student score derivative is the derivative of student u with respect to x.
And this derivative proves that on the positive half, it only crosses the zero line once.
Yes, the super-level set hypothesis kicks in, and the hazard rate order is salvaged.
Incredible. And what about examples 4.4 and 4.5? The zero inflated Poisson exponential models.
A zero-inflated model is like taking a normal smooth curve and dumping a massive spike of probability exactly on the zero mark.
Like modeling a factory where it either has a normal amount of defects or it's totally shut down with exactly zero defects.
Precisely. And that massive spike at zero shatters the likelihood ratio order. The kernel zigzags wildly at the start.
So if the line dips, the strict order is dead. How does he save it?
He routes the logic around the broken 0 point using conditional expectations.
Wait, so he just says, what if we only look at the probabilities of 1 or greater?
Yes. By conditioning on the value being at least 1, he mathematically blinds the equation to the zero anomaly.
That is a surgical bypass.
Yeah.
And the rest of the curve behaves perfectly. That covers section 4.2. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to section 4.3.
All right, section 4.3 looks at joint parameter and interpolation paths. This is where we use the chain rule in equation 14.
Up until now, we've only turned one dial at a time. But what if you need to turn the mean dial and the variance dial simultaneously?
Right, like reversing a diagonal path on the soundboard.
Exactly. The chain rule in equation 14 just adds the individual kernel slopes together, weighted by how fast you are turning each dial.
And he applies this in examples 4.6 through 4.9. Beautiful. That covers section 4.3. Have we missed any nuances?
I think we've thoroughly unpacked it. So let's proceed to sections 4.4 and 4.5.
Pairwise kernels and compound applications. Let's start with pairwise. How do you compare two completely different distributions?
By creating a log factor ratio interpolation, he basically builds a mathematical slider that morphs one formula into another.
And he applies this to the CATS class of distributions in example 4.9.
Right, using discrete second-forward differences to check concavity across entirely different families, like comparing a Poisson to a binomial.
It unifies the discrete probability universe. And then we hit example 4.14, compound applications.
This is where we see the payoff of that Bayesian trick from earlier. He analyzes compound Poisson, geometric, and negative binomial laws.
But there's a huge twist here. The compound Poisson goes one way, but the compound geometric flips its ordering direction. Why?
It's all about what the dial actually represents in reality. For a Poisson, the parameter is a rate. Turn it up, you get more accents.
Right, so the kernel slope is positive, risk goes up.
But for a geometric distribution, the parameter is the probability of success.
Ah, so if you turn the success probability up, you succeed faster, which means you accumulate fewer failures.
Exactly. The math detects the physical reality of the dial. The kernel slope becomes negative, perfectly mirroring the real-world logic.
That is just phenomenal. That covers sections 4.4 and 4.5. Have we missed any nuances?
I think we've thoroughly unpacked it. We've reached the conclusion.
Which brings us to section 5, the summary of this massive journey.
Zakaria Derbazi has truly provided a skeleton key. We can definitively say that the score is the centered kernel.
And we can completely bypass integrating likelihood ratios by merely differentiating log factors.
It replaces brute force computation with localized geometric insight.
So, bringing this all back to you, the listener, you might be wondering, why should I care about majorants and convolutions?
Because your life is governed by these dials. Insurance premiums, bridge safety margins, epidemiological models.
Exactly. In a world drowning in data, finding the kernel, the purest mathematical signal of how a system's risk changes, is the ultimate shortcut to truth.
It mathematically guarantees that when we turn a dial, the risk profile is strictly moving in a safe direction.
Now, I want to leave you with a final provocative thought. something not explicitly covered in the text.
Oh, I like where this is going.
We've spent this whole time looking at stationary parameters. You turn a dial, you lock it, you check the kernel. But what if the parameters are alive?
You mean if the dials are constantly spinning on their own, like a stochastic process?
Yes. Think of a financial market crash or a mutating viral strain. The dial is a moving target.
Oh, wow. So if the static kernel gives us the geometry of risk, could we construct a dynamic kernel?
Exactly. A dynamic kernel using stochastic differential equations. Not just measuring the risk, but the acceleration of risk in real time.
Moving from the static geometry of probability to the fluid kinematics of risk. That is a staggering frontier.
Something for you to mull over the next time you look at a bell curve. Remember, it's not just about the average. It's about the shape, the tail, and the hidden kernel driving the chaos. Thank you for surviving the unabridged protocol and joining us on this deep dive. Keep questioning the math and keep looking for the order hidden inside the chance.
Welcome, everyone, to a brand new explainer. If you're someone who absolutely loves finding elegant, clean solutions to incredibly complex, tangled mathematical problems, you are in the exact right place. Today, we're taking a deep, unabridged dive into a fascinating and literally groundbreaking paper by Zakaria Derbazi from Queen Mary University of London, published in May 2026. The paper is titled Kernel Characterisations of Stochastic Orders within Parametric Density Families. Now, I know that title sounds like a massive mouthful of intense probability mathematics, but don't worry, we are going to unpack exactly how this paper provides a brilliant, simplified shortcut for one of the most notoriously messy calculations in statistics. We're going to take our time with this, assuming we have all the time in the world to really understand the foundations. Ben, my producer off camera, that covers the first paragraph of the introduction. Have we missed any nuances? I think we've thoroughly unpacked it. Let's proceed to the next fundamental question. Before we get into the heavy math, I want you to really sit and think about this provocative question. How do you actually rank pure randomness? It sounds like a total paradox, right? Randomness, by its very definition, is unpredictable. But in the real world, organizing and ranking this unpredictability is a massive, absolutely crucial challenge. Think about an actuary. These are the professionals who use math and statistics to assess risk in insurance and finance. If they are trying to figure out if one type of insurance claim is inherently riskier than another, or if a financial analyst is comparing two highly volatile, unpredictable investment portfolios, they can't just look at a single average number. A simple average completely ignores the extreme tails, the sudden spikes, the full chaotic shape of the risk. You need to compare the entire unpredictable nature of those probability distributions. You need a rigorous, mathematically sound way to rank them from least risky to most risky. Ben, that covers the core real-world application here. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the roadmap.
Here is our roadmap for today's explainer. Section 1 is ranking the unpredictable. Section 2 covers the math problem. Section 3 is enter the kernel. Section 4 details the 4 rules of ordering. Section 5 explores beyond simple models. And finally, Section 6 is the big takeaway. Section 1, ranking the unpredictable, making sense of risk. Okay, let's dive into this. To understand the solution Derbazi is presenting, we first need to understand exactly what we are trying to organize in all this mathematical chaos. This brings us to a foundational concept you literally cannot do advanced statistics without: stochastic order. Let's define this clearly. In simple terms, a stochastic order is the rigorous mathematical framework used by data scientists, actuaries, and statisticians to rank entire probability distributions. When you have two different statistical models of unpredictable events, a stochastic order tells you mathematically if one distribution is definitively larger, riskier, or more variable than the other across the board. It's the absolute bedrock of decision-making under uncertainty. Without it, you're just guessing. With it, you can mathematically prove that portfolio A will expose you to worst-case scenarios than portfolio B. But actually getting to that definitive ranking is usually a total headache. Ben, that covers the foundational definition of stochastic order. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the actual mathematical problem.
Section 2, the math problem, a messy calculation. The traditional way data scientists figure out these stochastic orders is, quite frankly, a messy, highly complex calculation. For a very long time, the gold standard for comparing two probability laws has been something called the likelihood ratio. Now let's slow down and really look at the stark contrast here between the old method and the new one. As Derbazi's paper points out, the likelihood ratio is incredibly messy. It's heavily bogged down by syntax. It requires calculating what we call normalizing constants. A normalizing constant is just a number you have to divide your probability function by so that the total probability adds up exactly to 1. It sounds simple, but mathematically, finding that constant often requires intense, multidimensional integration. It's a massive chore. What this paper proposes instead is the kernel criteria. Think of the likelihood ratio as a tangled, complicated knot of syntax and integrals, and the kernel criteria as a clean, direct, shape-based diagnostic tool. Ben, that covers the high-level contrast between the two methods. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to a practical analogy.
To really visualize why the traditional likelihood method is so unbelievably cumbersome, think about it like this. Using the likelihood ratio to test for stochastic ordering is like building an entire, fully furnished house just to see if the foundation fits on the lot. It's overkill, right? You have to calculate the full likelihoods, and you get totally bogged down in integrating these massive normalizing constants, what the paper formally refers to as the additive terms. It introduces all this unnecessary density-level noise into your workspace. You are doing way too much mathematical heavy lifting just for a quick diagnostic check of the basic risk structure. You just want to know the shape of the risk, not the exact square footage of the metaphorical curtains. Ben, that covers the house analogy and the pain points of the traditional method. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the solution.
So, we clearly need a shortcut, which brings us to Section 3. Enter the kernel, the detective shortcut. This is the true hero of Derbazi's paper. The crucial point is understanding what a kernel actually does in this statistical context. A kernel is essentially a stripped-down mathematical blueprint. It completely strips away all that centering noise, those annoying normalizing constants we just talked about, and focuses exclusively on the parameter-dependent factors. Let's get rigorous for a second. The paper discusses how the kernel relates to the score function. The expression for the score function is s of x theta equals the partial derivative with respect to theta of the natural log of the probability density function f of x and theta. The score function s of x and theta equals the partial derivative with respect to theta of the natural log of the probability density function f of x and theta. Derbazi notes that the kernel mathematically equals that score up to a specific additive term. By purposefully dropping that additive term, we bypass the need to integrate. We are left with a pure, workable blueprint that tells us everything we need to know about the core shape of the probability law. Ben, that covers a mathematical definition of the kernel and the score function. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to how we use this blueprint.
Section 4. 4 rules of ordering. Shape over syntax. Now that we have this stripped-down blueprint, how do we actually use it? This is where the paper creates a total paradigm shift, moving our focus away from calculating heavy syntax and towards simply looking at mathematical shapes. This brilliant unified framework shows how simple shapes instantly dictate complex stochastic orders. Instead of doing the heavy calculus of likelihood ratios, you literally just look at the kernel's shape. As we see here, monotonicity gives you the likelihood ratio order, concavity gives you relative log concavity, and 2 specific tail conditional inequalities give you the usual stochastic and hazard rate orders. It is beautifully, stunningly simple. It's a unified theory for diagnostic shortcuts. Ben, that covers the broad overview of the 4 rules framework. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to break down the first specific rule.
Let's dig into that first rule, because it is incredibly direct. If you extract the kernel for your parametric family, and you graph it, and its shape is simply monotonic, meaning it's just a line consistently going up, or mathematically speaking, it is non-decreasing across its support, you instantly have mathematical proof of the likelihood ratio order. That is literally it. No messy integrals, no calculating constants, just, does the derivative stay positive? Does the line go up? If yes, boom, you have ranked your distributions. Then, that covers the monotonicity rule. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the second rule.
The second rule is just as elegant. If you analyze your kernel blueprint and find that its shape is mathematically concave on its support, meaning the second derivative is negative and the shape bows outward like a dome or an upside-down bowl, that instantly gives you the relative log concavity order. Again, you bypass the traditional heavy math completely just by identifying that the blueprint has a simple concave curve. It changes an integration problem into a basic geometry/calculus 1 problem. Ben, that covers the concavity rule. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the real-world complications.
Section 5.
beyond simple models, real-world messiness.
As any working data scientist will tell you, real-world data isn't always a perfect line or a perfect curve. The models we actually use get messy. So how does Derbazi's short count hold up when we test its absolute limits? In reality, we often deal with non-monotone kernels. Let's digress into foundational concepts for a second. Take zero-inflated models, like zero-inflated Poisson or exponential distributions. A Poisson distribution models counts of events, like insurance claims. But in the real world, there's often an excess of absolute zeros. A ton of people make zero claims. This is called atom inflation, and mathematically, it breaks the monotonicity right at the origin point of the graph. That means that simple, global upward line rule we just learned won't work across the whole dataset because of that spike at zero. The same exact problem happens with the half-student distribution, where the kernel is actually unimodal. It goes up and then comes back down, meaning it's neither globally monotone nor concave. So does the shortcut just completely break here? Then, that covers the problem of non-monotone real-world data. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the solution.
Thankfully, the answer is no, it doesn't break. Derbazi introduces a brilliant, highly technical rescue tool called the super level set criterion. What is a super level set? Fundamentally, it's just the set of all input values where the function outputs a value greater than a certain threshold. What this criterion does is rely on those last two rules from our table, the tail conditional mean inequalities. Even if the overall global shape is broken at the origin by zero inflation spike, this criterion cleverly uses conditional logic focused only on the tail end of the data to establish the hazard rate and usual stochastic orders anyway. It completely rescues the shortcut, proving mathematically that it's robust enough for actual real-world messiness, not just textbook examples. Ben, that covers the super level set criterion and tail logic. Have we missed any nuances? I think we've thoroughly unpacked it. Let's proceed to compound models.
Let's move on and see how this builds into even more complex applications, specifically regarding compound laws, which the paper details in section 3.4. If you are dealing with compound sums, which is essentially the sum of a random number of independent variables, like an insurance company trying to calculate the total payout when both the number of accidents and the cost per accident are totally random, the traditional math usually gets nightmarish. But Derbazi proves something remarkable. The compound law magically inherits its kernel directly from the underlying counting law. By just taking the simple kernel of the base counting law in step 1, applying a posterior averaging identity in step 2, the entire massive compound law inherits a usable kernel in step 3. You can rank infinitely complex compound distributions without ever calculating their full messy likelihoods. Ben, that covers the inheritance mechanism for compound laws. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the conclusion.
Section 6. The big takeaway. A unified framework. We've covered a tremendous amount of ground, diving deep into the foundations of stochastic ordering. I want to highlight this direct quote from Zakaria Derbazi because it encapsulates the absolute core thesis of this entire work. The kernel lives at the level of parameter-dependent factors before centering produces the score. The absolute genius here is all about when you choose to do the mathematical work. By operating before centering, meaning before you force the math to add up to 1, before you add in all those nightmarish normalizing constants required for a standard score or likelihood ratio, you save massive, massive amounts of mathematical effort. It makes these criteria incredibly portable to multi-parameter paths and complex compound distributions. It's a triumph of working smarter, not harder. Ben, that covers the core thesis and the meaning of the quote. Have we missed any nuances? I think we've thoroughly unpacked it. Let's proceed to our final thought. By prioritizing shape over syntax, we get a unified, highly efficient framework for ranking the unpredictable. So, I leave you with this final provocative thought. Knowing that you can strip away the noise and just look at the raw parameter-dependent blueprint, how will you use these kernel shortcuts to streamline your own complex data models? Think about it. Thanks for joining me on this unabridged deep dive into Derbazi's fascinating work. Keep learning, keep questioning the old methods, and I'll catch you in the next explainer. Ben, that covers the final slide. Have we missed anything at all today?
No, I think we've thoroughly unpacked the entire paper. We are done here.
Welcome to the Explainer. Today, we're diving deep into Zakaria Derbazi's highly technical statistical paper on the kernel characterizations of stochastic orders. We are going to translate this complex math into a clean, visual blueprint for comparing probability distributions. If you deal with predictive modeling, actuarial science, or any field relying on heavy statistical modeling, the insights we're about to unpack are literally going to be a game changer for your workflow. And because we are operating under the unabridged protocol today, we have infinite time. We are going to deconstruct everything. We're leaving no stone unturned. Ben, that covers the introduction. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the fundamental problem.
Okay, let's dive into this by asking the absolute core question that actuaries and data scientists face every single day. How do you mathematically prove one risk is greater than another? Now, let's look at the why here. Why is this even a question? Well, on the surface, it sounds straightforward, right? Just look at the averages. But in the realm of probability, proving that one risk profile is inherently greater or heavier across its entire spectrum is mathematically intricate. You're dealing with curves, tails, and variances, not just single numbers. Ben, that covers the core question. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the roadmap.
Here is our visual roadmap for today. 1. The probability comparison problem. 2. Defining stochastic orders. 3. Enter the kernel shortcut. 4. The 4 geometric rules. 5. Testing familiar distributions. And finally, 6. Why this shortcut matters. Let's keep moving.
Section 1. The probability comparison problem, the clunky traditional method. Let's jump right into the setup. So let's completely deconstruct this text. Traditionally, proving one distribution is greater than another required calculating full likelihood ratios. Why? Because historically, that was the only robust way to compare two probability densities. But it's a clunky process, filled with mathematical noise. When you use the standard likelihood ratio, you are literally forced to drag along complex, messy normalization constants. And what is the strategic goal of a normalization constant? It just ensures the probabilities sum to 1. That's it. It doesn't actually tell you anything about the underlying shape or the true behavior of the data. It just sits there, making the derivative calculus an absolute nightmare to process, especially when you're comparing multi-parameter families. It obscures the geometric truth. Then, that covers the first major hurdle. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the definitions.
Section 2. Defining stochastic orders. The 4 key orders. We need to ground ourselves in the absolute basics of what we're measuring. Let's define our terms with extreme granularity. Stochastic orders. Why do we need them? They are the formal mathematical frameworks we use to rank and compare these risks. Think of them as a hierarchy of strictness. Like I said earlier, we aren't just looking at a simple mean or median. We are looking at the entire curve of the probability distribution to categorically mathematically state that one set of outcomes completely dominates another. You need different levels of strictness depending on how robust your proof needs to be. Ben, that covers the definition. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the specific mathematical expressions.
This brilliantly illustrates the 4 specific orders their body's paper focuses on. We must be incredibly precise here, so let's break down the notation step by step. The first expression type is the usual stochastic order indicator, less than or equal to subscript ST. This is your baseline, simply comparing survival functions. The second expression type is the hazard rate order indicator, less than or equal to subscript HR. This is a step up in strictness. The third expression type is the likelihood ratio order indicator, less than or equal to subscript LR. This compares the densities directly. The fourth expression type is the relative log concavity order indicator, less than or equal to subscript LC. This is the strictest condition where the log of the likelihood ratio itself must be concave. Ben, that covers the 4 key mathematical symbols and their strictness hierarchy. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the breakthrough.
Section 3. Enter the kernel shortcut, stripping away the noise. This is where we meet the absolute protagonist of our explainer. Let's trace back exactly what premises this new framework is built upon by comparing these two approaches side by side. On the left, we have the old way. It relies on full likelihood ratios, right? It includes all those complex, parameter-dependent additive constants we just talked about. It's mathematically heavy. But look at the right, the new way, the kernel. Why is this so revolutionary? Because it acts as an incredible shortcut derived from the log density score. It literally strips away the additive constants to reveal the pure geometric shape of the distribution. It isolates the risk's mathematical DNA. Instead of calculating the entire ratio with all its baggage, you just look at the core structure. Isn't that an absolute breath of fresh air for your modeling pipelines? Ben, that covers the comparison. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the formal definition.
Okay, extreme granularity time. Let's break down this definition word for word. What actually is the kernel? Formally, it's a function on the support, meaning the range of values where the probability is greater than 0, whose centered version under the current law equals the score. So what is the score? The score is simply the derivative of the log density with respect to the parameter. Let's ask why again. Why do we define it this way? Because taking the derivative of the log density naturally eliminates any multiplicative constants from the original probability function. They just vanish into thin air. So a kernel is essentially a function that equals the score, up to an additive constant. And because we literally do not care about that constant when evaluating the overall geometric shape, we can ignore it entirely. We are left with a drastically simpler equation. Ben, that covers the definition of the kernel and the score. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the geometric rules.
Section 4. The 4 Geometric Rules, Theorem 3.5 Unpacked. This is where abstract calculus magically turns into basic geometry. I want you to treat this table as your ultimate visual cheat sheet for Theorem 3.5. Let's deconstruct exactly how basic geometric properties of the kernel directly prove those complex stochastic orders we defined earlier. First row, look at the kernel shape. Is it non-decreasing, just going up? If yes, boom, you have immediately established the likelihood ratio order, or as we learned, the expression type less than or equal to subscript LR. Second row, is the kernel curve concave? If yes, you've mathematically proven relative log concavity, the expression type less than or equal to subscript LC. Third and fourth rows. What if we look at the tail conditional mean? If it's greater than or equal to the kernel at x, you lock in the hazard rate order. If it's greater than the expected value of the kernel, you've proven the usual stochastic order. Why is this so powerful? Because checking if a line goes up is infinitely easier than dividing two massive polynomial equations. Ben, that covers the Theorem 3.5 cheat sheet. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the exceptions.
Now we have to ask, what happens when things get messy? What if the global shape isn't perfectly monotone? What if the line doesn't just neatly go up the whole time? Well, Derbazi's paper cleverly introduces super-level set criteria and tail conditional mean inequalities to handle these tricky, non-monotone examples. Let's use a tangible example here. Imagine a zero-inflated Poisson model. This is used a lot in insurance, where you have a massive artificial spike of zeros, meaning no claims were filed, followed by a normal curve for the actual claim amounts. That continuous geometric curve is literally broken at 0. You can't just look for a simple upward slope everywhere. But by applying these specific tail conditional checks, you can bypass that broken start and still mathematically prove that one risk is stochastically greater than another. You aren't defeated by the zero inflation. Ben, that covers the non-monotone edge cases. Have we missed any nuances? I think we've thoroughly unpacked it, Alex. Let's proceed to some real-world distributions. Section 5. Testing familiar distributions. Applying the blueprint. Let's see how this actually works on the models you use every single day. Before we test specific distributions, we need to understand how parameters influence the density. Why? Because depending on how a parameter enters the density function, the kernel takes on a highly predictable, easy-to-test form. Look at the bullets. Is it a natural parameter from the exponential family? Is it a power, rate, or scale parameter? Is it a shape parameter, sometimes involving complex Spokane blocks? Or is it a simple location parameter, which just translates the curve left or right? The mathematical beauty here is that if you know the parameter type, you instantly know the framework of the kernel. For example, if it's an exponential family, the kernel is literally just the natural sufficient statistic. It's already there.
Ben, that covers the parameter influences. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the actual tests. Let's look at this table and deconstruct it row by row. Testing familiar distributions becomes almost trivially efficient. Take the Poisson distribution. Its parameter type is a power parameter. When you extract its kernel, you find it is simply an affine, non-decreasing line. Since it is cleanly non-decreasing, boom, you immediately guarantee a likelihood ratio ordering. Next, the gamma distribution. It relies on a shape parameter. Its kernel property drops out as a logarithmic curve that is, again, cleanly non-decreasing. Boom! Likelihood ratio proven. Finally, the log-normal distribution. It uses a location parameter, creating a translated, non-decreasing kernel. Proven again. We completely, 100% bypass the clunky likelihood ratio. We don't touch the normalization constants, we just look at the geometric property. Ben, that covers the familiar distributions. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to why this matters in the real world.
Section 6. Why this shortcut matters. Compound laws and actuarial science. Time to bridge the gap between pure math and applied science. Let's break down these 3 steps because they represent a massive optimization for actuarial science. In insurance modeling, you constantly deal with compound laws, like geometric jump models where you have a frequency of claims compounding with the severity of claims. It's a mathematical monster, but look at the steps. Step 1, identify the simple underlying counting law, like our friend the Poisson distribution. Step 2, extract the kernel of just that simple counting law. Step 3, the complex compound law inherits this kernel entirely automatically via posterior averaging. Let's unpack why this is a big deal. You literally do not have to calculate a convoluted, page-long equation for the compound distribution. You just look at the simple counting law, grab its kernel, and you can mathematically prove your stochastic order based on that inherited trait. It's like finding a backdoor in the math. Ben, that covers compound laws. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the paper's conclusion.
I want to read this quote from Derbazi directly, piece by piece. The score and kernel can be used interchangeably. Okay, let's pause. That establishes the core mathematical validity. You aren't losing precision by switching. While the kernel form often removes normalizing terms and leaves a simpler state-dependent expression. This right here is the true hero of the entire paper. The kernel form strips away the static noise. It leaves you with a highly workable, purely state-dependent expression. It essentially transforms what used to be a tedious, error-prone calculus exercise into a streamlined, highly elegant geometric proof.
Ben, that covers the core quote. Have we missed any nuances?
I think we've thoroughly unpacked it, Alex. Let's proceed to the final takeaway. I'll leave you with this final provocative thoughts. Think about your day-to-day work. How much faster could you optimize your own predictive models and data pipelines if you completely stopped calculating the noise and focused entirely on the shape of the risk? By adopting this exact kernel shortcut, you can make your statistical pipelines cleaner, significantly faster, and vastly more elegant. Ben, that covers the final slide. Have we missed any nuances?
No, I think we thoroughly unpacked the entire explainer, Alex. Thank you everyone for diving into the math with us today.
Welcome to this explainer. Today, we're diving deep into some seriously elegant mathematics. We're unpacking a fascinating paper by Zakaria Derbazi titled Kernel Characterizations of Stochastic Orders within Parametric Density Families. Now, if you're a quantitative analyst, a data scientist, or a statistician, you already know that comparing complex probability distributions is a daily hurdle, right? Well, Derbazi's paper offers a unified, highly efficient framework to tackle this exact problem, and we're going to break it all down for you. So let's address the elephant in the room. How do we efficiently compare complex probability distributions? When you're trying to figure out if one probability law is, greater than another, like comparing different hazard rates or likelihood ratios, the standard industry approach is just heavy. It's mathematically exhausting. You're usually forced to wrestle with cumbersome likelihood ratios that are an absolute pain to evaluate systematically, especially when you're looking across large parametric density families. It's a massive bottleneck. Here is our roadmap for today's explainer. We'll start with the distribution comparison problem. Define scores and kernels, map out the 4 stochastic orders, handle non-monotone kernels, explore compound laws, and finally, wrap up with the unified toolkit. Let's jump right into section 1, the distribution comparison problem. Establishing stochastic orders between parametric families is one of the most frequent, yet honestly frustrating challenges in quantitative analysis. Why? Because the status quo has a major flaw. The traditional literature relies really heavily on the likelihood ratio to establish these stochastic orders. If you want to prove likelihood ratio order, relative Lau concavity, hazard rate, or usual stochastic order, you're traditionally stuck computing and analyzing the exact shape of the likelihood ratio. And when you're dealing with large density families, those likelihood ratios become incredibly complex and practically impossible to analyze efficiently. We absolutely need a shortcut here. Moving on to section 2. Defining scores and kernels. Let's break down the mathematical anatomy of this elegant shortcut. First up, we really need to understand the score. For densities that are differentiable in their parameter, the score is simply the derivative of the log density with respect to that parameter. Now, mathematically, the score is incredibly precise, no doubt about it. It's centered under the current probability law, which means its expected value is exactly 0. But here's the catch. That centering constant makes the score super bulky and really cumbersome to work with algebraically. And that is exactly where the kernel enters the chat. The kernel is the real hero of our explainer today. Simply put, a kernel is a function that equals the score up to an additive term that depends only on the parameter. By doing this, the kernel just throws out that bulky centering constant. It isolates the pure, unadulterated effect of the parameter on the distribution. It's so much simpler to evaluate because it literally strips away all that mathematical noise. Zakaria Derbazi puts this brilliantly in the paper. He writes, "The kernel lives at the level of parameter-dependent factors before centering produces the score. Think of the kernel as the literal DNA of the distribution's parameter. Because it exists before that whole centering process, it's highly portable. We can use it to compare joint parameter paths, pairwise factor forms, and even those really complex compound laws." Which brings us to Section 3, the 4 stochastic orders. This is where the abstract algebra translates into incredibly powerful geometric rules. Derbazi's paper proves that you can completely bypass the likelihood ratio and just look at the geometric shape of the kernel itself. Just look at how beautifully this maps out. If the kernel is monotonically increasing or decreasing, boom, you immediately get the likelihood ratio order. If the kernel is mathematically concave, you get relative log concavity. And if the kernel satisfies 2 specific tail conditional mean inequalities, you unlock the hazard rate and usual stochastic orders. It is just so beautifully simple. So, you're probably wondering, how do I actually apply this workflow in my own modeling right now? It's literally a 4-step process. Step 1, identify the parameter-dependent factor of your density. Step 2, take the derivative of its log to extract your kernel. Step 3, check the geometric shape of that kernel, like is it monotonic, is it concave? And finally, step 4, map that shape to the corresponding stochastic order using the cheat sheet we just talked about. 4 simple steps, and you've just replaced pages of tedious likelihood ratio calculus. All right, let's look at Section 4, handling non-monotone kernels. But of course, we all know the real world is messy, right? What happens when your kernel isn't perfectly monotonic or concave across the entire support? While we have those global shape rules for perfect monotonicity, the paper introduces an amazing safety net for when those fail. It's called the super level set criterion. It mathematically proves that even if global monotonicity is broken, as long as the kernel meets certain tail conditional checks, you can still perfectly rescue and secure both the hazard rate and usual stochastic orders. To put that into perspective, let's look at some specific examples from the paper, like the half-student distribution, the zero-inflated Poisson, or the zero-inflated exponential. In zero-inflated models, that atom inflation at the origin completely breaks perfect monotonicity. The global rules just fail. But by applying Derbazi's tail conditional checks, we can still establish robust hazard rate and stochastic orderings for these messy, real-world distributions. It's a real game changer. Moving right along to Section 5, compound and joint parameter laws. This is where we really see just how portable these kernel criteria are. If you're working with discrete compound laws, say a random number of independent and identically distributed terms, it sounds like an absolute nightmare to order them, but Derbazi reveals that, quote, the compound law inherits a kernel from the underlying counting law through a posterior averaging identity, end quote. What does this mean for us? It means you don't need to analyze the whole compound mess. You simply take the posterior mean of the original counting law's kernel. The math just beautifully cascades down. And the data backs this up perfectly. For compound distributions where the underlying counting law is Poisson or binomial, the kernel slope is positive, which dictates a standard likelihood ratio direction. But for geometric counting law, the slope is negative, and the likelihood ratio order perfectly reverses itself. So literally, just by checking the slope of the kernel, you instantly know the likelihood ratio direction for incredibly complex compound distributions. How cool is that? And it extends even further than that. If you're doing joint parameter comparisons, like interpolating paths between 2 probability laws with distinct factor forms, you can use the algebraic log ratio of the factors directly as your path kernel. You get to completely skip all those cumbersome likelihood calculations and jump straight to the answer. Finally, Section 6, the Unified Distribution Toolkit. Let's bring all this abstract algebra back down to earth for a second and look at Derbazi's catalog of continuous distributions. For the gamma distribution in its rate parameter, the kernel form is simply -x, which is naturally decreasing. The beta distribution's first shape parameter gives a decreasing kernel form of 1/x, and the Pareto distribution gives an increasing kernel form of -1/x. You no longer have to guess or do the calculus from scratch every single time. The core geometry of these classical distributions has been distilled right down to these simple kernel forms. So let's quickly summarize the core value proposition of what we've unpacked today. Derbazi has given us a highly portable toolkit. It unifies four major stochastic orders into a single, elegant geometric framework. It completely replaces the need for complex, heavy likelihood ratios. And on top of all that, it's robust enough to handle non-monotonic subends, compound laws, and joint parameter paths. This is, without a doubt, a massive upgrade in efficiency for any quantitative analyst. Which leaves us with one final thought to ponder. How will kernel criteria simplify your next density family analysis? The next time you find yourself bogged down in algebraic likelihood calculations, just remember that there is a simpler, much more elegant geometric path waiting for you in the kernel. Thank you so much for joining me on this deep dive. Go apply this mathematical shortcut, and I'll catch you on the next explainer.